Welcome to another deep dive. Today we're looking at this paper by V. Gladkova on induced arithmetic removal.
Okay. Sounds.
It's a pretty dense paper, but I think there's some really cool stuff in here.
Yeah.
Even for those of us who aren't, experts in this specific area.
Absolutely. Gladkova is really tackling kind of a fundamental question in this paper.
Okay.
Can we completely remove certain arithmetic patterns from a vector space over a finite field just by recoloring a small part of it?
Like a little bit.
Yeah.
So that's kind of the overarching question.
Yeah. And it sounds like the answer is tied into this idea of partition regularity.
Right.
Which I got to admit, I'm a little fuzzy on.
Well, so partition regularity, you can think of it this way.
Okay.
Imagine coloring the elements of a vector space over a finite field. Partition regularity essentially means that no matter how you color the space, certain patterns are guaranteed to appear. So no matter how you slice it up, there are certain combinations that are just unavoidable.
Right.
I'm starting to see why that's relevant to the whole removal problem.
Yeah.
Yeah.
So Gladkova focuses specifically on partition regular patterns of complexity 1.
Okay.
So these patterns are defined by linear forms.
Okay.
You can think of them as sets of points that satisfy a specific linear equation, and each point has a color assigned to it.
Gotcha.
And complexity 1 just means that we're looking at a simple linear relationship.
All right, so we've got our colored space and then these unavoidable patterns.
Right.
But when we say remove them, what does that mean?
So imagine you have a network.
Okay.
And you want to get rid of all the triangles in the network.
Okay.
But you can only change a few connections.
Okay.
That's kind of analogous to what we're doing here.
Right.
If we have a space where a specific arithmetic pattern appears very infrequently, can we tweak the coloring just a little bit?
Just a tiny bit.
To make that pattern disappear entirely. And previous work on this problem couldn't quite get to complete removal. There were always some exceptions.
So Gladkova is pushing the boundary of what's possible with this induced removal.
Exactly.
All right.
Specifically for these partition regular patterns.
All right, cool. And the key to their approach here is this thing called the arithmetic regularity lemma.
That's right.
Okay, what is that?
So imagine you're looking at a giant canvas that's been splattered with different colors. The arithmetic regularity lemma basically helps us divide this canvas into neat, well-behaved sections, each with a predictable distribution of colors.
Bringing order to chaos.
Exactly.
But how do we actually use that order to get rid of the patterns?
Well, Gladkova introduces this new strategy for selecting specific subcosets within these regular sections. You can think of it as choosing kind of the perfect representative swatch from each section of our canvas.
Gotcha.
The key is to choose subcosets that not only have these nicely distributed colors, but also accurately reflect the potential patterns that are hidden within each section.
Okay, I'm starting to see how this is all coming together.
Yeah.
So by carefully picking these representative subcosets, we can analyze them.
Exactly.
We can understand the pattern's behavior and then recolor strategically.
Yeah. And the way Gladkova chooses these subcosets is a two-stage process. And it draws inspiration from techniques that are used for induced removal in graphs. And this two-stage process gives us a lot of control over the properties of the subcosets.
All right, so we can pick some really good ones.
Exactly.
That'll help us do what we need to do.
Yeah.
Okay.
Yeah.
This is pretty cool. Can we dive into some of the specifics of the proof?
Sure.
I'm curious to see how this two-stage selection process actually works.
Absolutely. So let's start by taking a closer look at proposition 5.1 in the paper.
Okay.
This proposition essentially describes the first stage of the subcoset selection process.
Right.
It essentially states that given any set of colors in our space, we can find a set of subcosets that meet 3 crucial criteria. And these subcosets are represented as sub2 sub plus u, where hes sub2 sub is a specific subspace and u is a vector. And the first criterion is that hes sub2 sub. And its containing subspace, denoted by hes sub 1 sub, have codimensions, denoted by d sub 2 sub and d sub 1 sub, respectively, that are bounded by some constant c sub brig sub.
Okay.
And this constant C sub reg sub depends on our desired level of accuracy and the number of colors we're working with.
Okay.
And codimension in this context is just a way to measure how much smaller a subspace is compared to the entire vector space.
So we're making sure our subspaces are a decent size.
Exactly. We don't want them to be too tiny.
Right.
The second criterion is that for almost all non-zero elements, the subcoset h sub 2 sub plus u is a regular.
Okay.
And the parameter here represents our desired level of uniformity in the color distribution within the subcoset.
So we want the colors to be nicely mixed.
Exactly.
In our subcosets.
Right.
Okay, cool.
Yeah.
And you mentioned Fourier uniformity earlier.
Yeah, Fourier uniformity actually plays a crucial role here in quantifying how well distributed the colors are.
Okay.
Yeah.
Gotcha. All right, so we've got these subspaces. The colors are nicely mixed within them.
Right.
What's the third criterion?
The third criterion ensures that the color densities on almost all of these subcosets, sub 2 sub plus u, closely approximate the color densities of the larger coset h sub 1 sub plus u, which they are contained within. So this is ensuring that our subcosets are good representatives of their parent coset.
So our swatches are accurately representing the bigger section.
Exactly.
Cool.
Yeah.
Okay, so that's Proposition 5.1.
Yeah, that's the essence of Proposition 5.1.
It gives us a way to find these well-behaved subcosets with nicely mixed colors that are representative of the parent cosets.
Exactly.
Pretty cool.
Yeah, it lays a good foundation.
Yeah. I feel like we've laid a really strong foundation here.
Yeah.
But there's still a lot more to uncover.
Right. This is just the first stage.
This is just the first stage.
Of the subcoset selection process.
Okay, so we're going to have to come back.
Yeah, we're going to have to come back.
For part 2 to hear about the second stage.
Exactly.
All right, I'm excited for that.
Yeah.
But we'll leave it there for now.
Sounds good.
And pick it up next time.
Yeah. Yeah.
All right, so we left off talking about this idea of partition regularity. And we had that first stage of Gledkova's subcoset selection process.
Yeah.
I'm ready to dig into the second stage.
Okay. Excellent.
What happens in stage 2?
So recall that Proposition 5.1 gave us a set of subcosets.
Okay.
Denoted as sub 2 sub plus u.
Right.
That met our 3 criteria.
Yeah.
You know, the bounded codimensions, the regularity, and the accurate representation of parent cosets.
Yeah, they were good subcosets.
Exactly. But we still need to refine our selection within a specific coset.
Okay.
Namely, the zero coset of ho sub 2 sub.
Okay, why the zero coset? Why is that special?
The zero coset plays a really unique role in this whole process.
Okay.
It's the coset that contains the zero vector.
Okay.
And its structure is really crucial.
Okay.
For ensuring that our final recoloring truly eliminates all instances of the pattern.
Okay. Got to make sure we get everything.
Exactly. We don't want to miss anything.
Right. Yeah.
So this is where lemma 5.3 comes into play.
All right. What's lemma 5.3 all about?
So this lemma states that within the zero coset of Hayes sub 2 sub, we can find even smaller subcosets.
Even smaller?
Yeah, we're going even deeper.
Okay.
Denoted as H plus sub J sub.
Okay.
Where H is a subspace of Hayes sub 2 sub, and the sub J sub are specific vectors chosen from Hayes 2 sub.
Okay.
And these subcosets have to meet some pretty specific conditions.
All right, so what makes these subcosets so special?
The first condition is that they have to satisfy the partition regularity condition of our target pattern, which means that they have the potential to contain an instance of the pattern.
Right. So they could have the pattern.
Exactly.
Okay.
The second condition is that the smaller subcosets, H plus sub J sub, need to be even more uniform.
Even more uniform?
Yeah, even more uniform than the subcosets that we selected in the first stage.
Okay, so the colors are even more evenly distributed.
Exactly.
Cool.
And then finally, the third condition is related to the density of the colors. For each color, its density on these subcosets has to be either consistently high or consistently low.
Okay, so no in between.
Exactly. It's either all in or all out.
Okay, got it. And how does that help with the recoloring?
Well, this clear separation is really crucial because it allows us to make very decisive choices. During the recoloring process, we'll replace colors that have low density in these subcosets with colors that have high density, effectively eliminating the possibility of the pattern forming.
Gotcha. So we're basically getting rid of any chance of the pattern showing up.
Exactly.
Okay. Yeah, we're being very strategic about it.
It's like we're playing whack-a-mole. with these patterns.
Exactly. You could say that.
Okay, but I gotta admit, I'm still having a little trouble picturing all this.
Yeah, it could be a bit abstract.
Can you help me visualize it a bit better?
Sure. Imagine you have a mosaic.
Okay, like a tile mosaic?
Exactly. Made up of tiny tiles of different colors.
Okay.
Each tile represents an element in our vector space.
Okay.
And the color of the tile represents the color assigned to that element.
Gotcha.
So the overall pattern of colors in the mosaic represents the initial coloring of our vector space.
Okay, so where do the subcosets fit into this?
The larger cosets from Proposition 5.1 are like sections of this mosaic, each with a distinct pattern of colors.
Right.
And the smaller subcosets from Lemma 5.3 are like tiny representative samples from each section.
Tiny little swatches.
Exactly.
Okay.
And by analyzing the color distribution within these samples, we can infer the color distribution within the entire section.
So it's like if our little sample has very few blue tiles,
Right.
we can guess that the whole section probably doesn't have many blue tiles either.
Exactly.
Yeah, okay.
And then we can make a decision about whether to replace those blue tiles with a different color during recoloring.
Okay, so that's how we use the subcosets to guide our recoloring strategy.
Precisely.
Okay, that's a really helpful analogy.
Yes, I'm glad that makes sense. But we're still dealing with multiple colors here.
Right.
Not just black and white.
Yeah, it gets a bit more complex.
How do we handle that?
So Gladkova introduces a clever way to represent these multiple colors mathematically using a set of functions denoted by subi sub, where each function corresponds to the distribution of a specific color.
So each color gets its own function.
Exactly.
Okay.
And this allows us to treat each color independently and analyze its behavior within these chosen subcosets.
Gotcha. So we can look at each color individually and see how it's spread out.
Yeah, exactly. And with these functions in hand, we can formally define the recoloring scheme.
All right, so how does that work?
This is where Lemma 5.4 takes center stage.
Okay, what does Lemma 5.4 tell us?
So Lemma 5.4 essentially states that we can construct a new coloring, which we'll denote by theorem, that differs from our original coloring in only a small fraction of the space.
So we're only changing a few tiles in our mosaic analogy.
Precisely.
Okay.
But crucially, this new coloring has a very specific property.
Okay, what is it?
If a color appears in any colset under her, it must have high density on the representative subcosset chosen for that colset.
So any color that makes it through the recoloring process has to be well represented.
Exactly.
In our little swatches.
It all ties back to those swatches.
Yeah, very strategic.
It is. And by combining this property with the counting lemma and those carefully chosen subcossets, Gladkova shows that this new coloring has absolutely no instances of the target pattern.
So we actually achieved complete pattern removal.
We did it.
Wow, that's amazing.
Yeah, it's pretty remarkable.
I'm starting to really understand how all these pieces fit together.
Yeah, it's all about strategically using these tools and concepts.
So we've got the subcosset selection.
Right.
We've got the color density functions. And then Lemma 5.4 that ties it all together.
It all comes together beautifully.
Yeah, it really does. But I feel like we've only scratched the surface here.
Yeah, we have.
There's still so much more to explore.
There's a lot more depth to Gladkova's work.
Like what?
Well, the paper goes on to rigorously prove this result in Theorem 5.5.
Yeah.
Building on all the lemmas and propositions we've discussed.
Yeah, I want to hear all about that.
We'll definitely dive into that in the next part.
Okay. I'm excited to get into the nitty-gritty of the proof.
Yeah, let's get to the heart of it.
All right. But for now, we'll leave it there.
Sounds good.
Okay, so we've talked about partition regularity, we've gone through the subcoset selection, and we've seen how the recoloring strategy works.
Right, we've laid all the groundwork.
Yeah, now let's get to the heart of it all, the actual proof itself.
All right, time to dive into Theorem 5.5. Where Gladkova formally proves that for any partition regular pattern of complexity 1, we can find a recoloring that eliminates the pattern entirely.
Given that its initial density is low enough? All right, so let's see how all these pieces come together.
Okay, so the theorem starts by assuming we have a partition regular pattern, which is represented by a matrix A. This matrix essentially encodes the linear relationships that define the pattern.
Gotcha.
We also assume we have an initial coloring of our vector space, denoted by where the pattern appears with a density below a certain threshold.
So the pattern's not too common.
Exactly.
Okay, then what?
We then apply lemma 5.4, which we talked about earlier.
Right, the one that gives us that special recoloring.
Exactly. So this lemma gives us a recoloring and a set of nested subspaces. Sub 3 sub, hes sub sub, sub nu sub, sub 1 sub, along with the complement u. And these subspaces, together with the complement, form kind of the structured framework within which we can analyze the recoloring.
So sub 3 sub are like those miniature swatches we talked about.
Exactly, the ones with those highly uniform color distributions and consistent pattern potential.
Okay, so how do we actually prove that this new coloring has no instances of the pattern?
The proof proceeds by contradiction. Classic contradiction.
So we assume, for the sake of argument, that there is an instance of the pattern under cat.
Exactly. This means there exists a set of points, which we'll denote by sub 1 sub up to yi sub sub, that satisfy the pattern's linear equations as encoded by the matrix A. Additionally, their colors under ooze have to match one of the allowed color combinations.
Okay, so it has to be a legitimate instance of the pattern.
Exactly. We're not cheating here.
Right. Okay, what's next?
We then decompose each of these points, the u subi subs, as the sum of two components. An element u subi sub from the subspace plus sub 1 sub, and an element u subi sub from the complement u.
Okay, so we're breaking down each point into two parts.
Exactly.
One in sub 1 sub and one in u.
Precisely, and this is possible because shu sub 1 sub and u together span the entire vector space.
Gotcha, so every point could be expressed that way.
Right, and why is this breakdown helpful?
Yeah, why do we care?
It allows us to shift our focus from the original points, the subi subs, to a new set of points that involve the complement u. And those special points, subi sub from lemma 5.3.
Right, those carefully chosen ones.
Exactly. So we consider the points u sub 1 sub plus sub 1 sub up to u sub sub plus sub sub. Now, because the subi subs form an instance of the pattern, and the subi subs were chosen to also have potential for the pattern, this new set of points must also form an instance of the pattern.
Okay, so we've shifted our attention to these new points.
Yes, and this shift is crucial.
Why?
Because now we can apply the counting lemma to the subcosets h sub 3 sub plus u subi sub plus subi sub.
The miniature swatches.
Exactly. Remember, these subcosets were carefully selected.
Yeah, they had those nice properties.
Right. They were consistent with the pattern, and they had well-distributed colors under the original coloring.
Okay, so what does the counting lemma tell us about these subcosets in this scenario where we're pretending the pattern still exists?
It tells us that the density of the pattern within these subcosets must be at least some positive value. And this value is determined by the level of uniformity and a constant that depends on the pattern itself.
So even though we're working with the recoloring, where we assume the pattern is gone, the counting lemma suggests that the pattern should still exist in these subcosets.
With at least some noticeable frequency.
That sounds like a contradiction.
It is a contradiction.
Because we assume the pattern was gone.
Right. This contradicts our initial assumption.
So our assumption that the pattern still exists under era must be wrong.
Exactly.
Wow. So by setting up this whole framework of subspaces and subcosets and using the counting lemma, Gladkova shows that the recoloring actually does eliminate the pattern.
It's a very elegant proof.
It really is.
Yeah.
It's amazing how all these tools come together.
It highlights the power of these mathematical concepts.
Yeah, and it's not just about the proof itself.
Right.
It's about the bigger picture.
This result has implications for other areas of math and even beyond.
Like what?
Well, think about data analysis. Network optimization. Even cryptography.
Yeah.
Understanding how to get rid of unwanted patterns can lead to more efficient algorithms, more robust systems, even more secure communication.
It is pretty mind-blowing.
It really shows how abstract math can have a real-world impact.
Well, folks, that brings us to the end of our deep dive.
It's been a pleasure exploring these ideals.
We've gone through a lot today.
We have.
From partition regularity to subcoset selection.
To the proof it's...
To the broader implications of Gladkova's work.
It's been quite a journey.
Hopefully you've enjoyed it as much as we have.
I know I have.
And remember, even the most complex math can be understood.
With a bit of patience and curiosity.
So keep those minds curious.
Absolutely.
And stay tuned for more deep dives into the world of knowledge.
We'll see you next time.
Until then. Welcome back, everyone. Today's deep dive takes us into the fascinating realm of induced arithmetic removal. We're going to be dissecting this recent paper. It's called Induced Arithmetic Removal for Partition-Regular Patterns of Complexity 1. And, this area of mathematics can get pretty complex, but this paper dives right in and tackles some big challenges.
Yeah, it really does. When I first saw this paper, I was immediately drawn to how they achieve complete removal of specific arithmetic patterns. It's something that previous work using traditional induced removal lemmas has really struggled with. Those older methods never quite got there. You know what I mean?
Yeah, totally. It's almost like you're trying to completely untangle a knot. No matter how hard you try, there always seems to be that one stubborn little snag that just won't come undone. But these researchers, they've found a way to address that head on. But before we get into their solution, let's take a step back and lay some groundwork. The paper uses a familiar example from graph theory, triangle removal, to kind of introduce the whole concept of arithmetic removal lemmas. Can you break that down for us a bit?
Of course. So in graph theory, we have these things called triangle removal lemmas. And these lemmas, they basically say that if you have a graph with, let's say, a small number of triangles, well, you can remove all of them by making just a few changes to the edges in the graph. Now, arithmetic removal lemmas kind of follow a similar logic, but instead of graphs, we're dealing with vector spaces over finite fields. And instead of removing triangles, we're aiming to eliminate specific arithmetic patterns within these spaces.
Gotcha. So instead of messing around with edges, we're changing colors to kind of disrupt these patterns. But like you mentioned earlier, the traditional methods couldn't always guarantee complete removal. There were always a few stragglers hanging around. And that's where this paper steps in, right? They've introduced this new lemma that actually does achieve complete removal, at least for a specific kind of pattern. But before we dive into that, let's talk about the whole concept of arithmetic patterns. The paper defines these in definition 1.1. What are they exactly?
Well, imagine you have this vector space, right? And you've colored all the elements in this space using a certain number of colors. Now, an arithmetic pattern is essentially a specific arrangement of these colors within the vector space. It's defined by two things: linear forms, which are basically like equations, and color assignments, which tell you which colors should appear where.
Okay, so we're looking for specific color combinations that satisfy certain equations within the vector space. Makes sense. Now, the paper also introduces this idea of partition regularity in definition 1.3. What does that mean exactly? I always get a little tripped up by that concept.
Well, yeah, partition regularity. Think of it this way. Let's say you have a linear system of equations, something like, x equals 0. Now, partition regularity essentially asks, no matter how you color the elements of your vector space, can you always find a solution to that equation where all the variables have the same color?
So it's like a guarantee that no matter how you paint your vector space, you'll always find a monochromatic solution to that specific equation. Pretty neat, huh? But what happens when a pattern isn't partition regular? What then?
That's where things start to get a bit tricky. The paper illustrates this with example 1.4. Basically, if a pattern isn't partition regular, it means that there's a way to color the vector space so that you can't find a monochromatic solution except maybe for the trivial 0 solution. And no matter how you try to recolor things, that pesky 0 solution might stick around, preventing complete pattern removal.
It's like trying to wipe away a stain that just keeps reappearing no matter how hard you scrub. Okay, so this is where the paper really makes its move, right? They introduce a new induced removal lemma, which is theorem 1.5, and this one actually guarantees complete removal of partition regular patterns. But there's a catch, right? It only works for patterns of complexity 1. What does that mean? Complexity 1.
Yeah, good catch. Complexity 1 basically refers to patterns that are defined by a single linear equation. Think of it as the simplest kind of pattern you can have in this context. And what the paper shows is that for these specific patterns, if they're partition regular, then you can actually achieve complete removal.
So they've kind of cracked the code, at least for this particular type of pattern. And to show how this all works in practice, they use example 1.6. This one deals with getting rid of, what do they call them? Rainbow solutions in an equation. What's so special about this example? Why did they choose it, do you think?
It really highlights the strength of their new lemma. You see, a rainbow solution is basically one where all the variables in the equation have different colors. And previous lemmas, they really struggled to completely eliminate these specific color combinations. But with this new lemma, complete removal becomes possible. So it's a really nice demonstration of how this new approach can handle situations where the older methods kind of fell short.
It's like they've found a more precise tool, right? One that can really zero in on those specific color combinations and eliminate them. Very cool. Now, the paper then goes on to explore some of the broader implications of this new lemma. And this leads to corollary 1.7. What does this corollary tell us? About vector spaces, I mean.
So corollary 1.7 essentially says that if you have a subset of a vector space, that subset has to satisfy one of three conditions. It's either small, it has a certain density of sums outside the subset, or it's very close to being a subspace itself. And this reveals a fundamental structural property of vector spaces, a property that kind of emerges from this new induced removal lemma.
Wow, so it's not just about removing patterns, is it? It's about understanding the very fabric of these mathematical objects.
Yeah.
Okay, now let's shift gears and talk about the proof itself. They use this powerful tool called the strong arithmetic regularity lemma. Can you give us a quick overview of how that works?
Sure. Imagine you have this vector space, right? And it's all messy and disorganized with colors scattered all over the place. Now, the strong arithmetic regularity lemma is like this amazing organizing principle. It lets you partition the vector space into these nice, well-behaved pieces called cosets. And within these cosets, the colors are distributed much more evenly.
It's like tidying up a messy room and putting everything into neat labeled boxes. But the real breakthrough in this paper, at least from what I understand, is how they select subcosets within these partitions. They call it the subcoset selection strategy, and it's quite different from what's been done before.
You got it. Previous methods usually just picked one subcoset from each of these coarser partitions. But this new method, it actually allows for the selection of multiple subcosets within each partition. And this gives them a crucial level of flexibility.
So instead of just picking one representative from each box, they're carefully choosing a small group of representatives that best capture the overall distribution within the box. Smart. And this added flexibility, which they illustrate in figures 3 and 4, is really key to achieving both regularity and pattern consistency across the whole space.
Exactly. By choosing multiple subcosets, they can make sure that the recoloring process doesn't mess up the underlying regularity of the space, while at the same time aligning the colors in a way that disrupts the target pattern. It's a delicate balancing act, for sure.
And this leads us to the heart of the proof, which is section 5. Things start to get a bit more technical here. But to set the stage, they establish a crucial link between linear systems and partition regularity. And this connection is rooted in something called Raddo's column conditions. Can you tell us a bit about those and what role they play?
Of course. So Raddo's column conditions provide a criterion for determining whether a given matrix is partition regular. Think of it as a set of rules that help us identify the specific types of patterns that have this special partition regularity property. Essentially, they dictate specific relationships between the columns of the matrix that guarantee the existence of monochromatic solutions to the corresponding linear system.
So it's like a checklist, right? To make sure that our pattern will always have a foothold in the vector space no matter how we try to color it.
Yeah.
Very cool. They then introduce lemma 5.3, which I understand plays a pretty big role in making sure we can always find subcosets with the right properties. Can you walk us through that lemma a bit?
Sure. Lemma 5.3 basically guarantees that we can always find subcosets that are both regular with respect to our coloring and also aligned in a way that respects the structure of the pattern we want removed. It's like finding the perfect set of building blocks that will fit together to create a structure where the pattern just can't exist.
So it's like having a blueprint that guides you towards the right combination of subcosets. And then all of this comes together in lemma 5.4, which outlines how to actually construct a recoloring that guarantees the complete removal of the target pattern.
Exactly. Lemma 5.4 is where the magic happens. It shows us how to carefully manipulate the colors using those specially chosen subcosets to create a new coloring where the pattern is completely gone. And this whole process involves analyzing the color densities on those subcosets and strategically replacing colors to break up the pattern's formation.
It's like a beautifully choreographed dance of colors where each step is designed to dismantle the pattern without disrupting the overall harmony of the space. Okay, so with lemma 5.4 in hand, we're now ready to tackle the final stages of the proof, which leads us to the main theorem itself, theorem 5.5.
Absolutely. Theorem 5.5 is where everything comes to a head. It basically says that for any partition regular pattern of complexity 1, if you have a coloring with a low enough density of that pattern, then you can find a recoloring that completely wipes it out. So essentially, if the pattern is sparse enough to begin with, we have the tools to make it disappear entirely.
Wow, that's quite a statement. But how do they actually prove this? I'm especially curious about how they connect lemma 5.4, which is about constructing this specific recoloring, to this broader claim of complete pattern removal.
Well, they use a pretty classic proof by contradiction. They start by assuming that there's still a sneaky instance of the pattern hanging around in the recolored vector space. Remember, this instance would have to satisfy a certain equation, like I equals 0, where A is our matrix representing the pattern's dependencies.
So it's like saying, okay, let's pretend for a moment that the pattern hasn't been completely eliminated. What would that mean?
Exactly. And then the proof uses the properties of their special recoloring, especially the fact that if a color shows up in a coset under the new coloring, it must have been pretty common on the representative subcoset under the original coloring. And they use this to show that if the stubborn instance of the pattern really exists, it would mean that the pattern was actually much more prevalent under the original coloring than we thought.
So it's like, if the pattern managed to survive the recoloring, it must have been a lot stronger before we started messing with the colors.
You got it. And to really nail down this argument, they turn to the counting lemma. This lemma helps them estimate how many instances of the pattern there would have been under the original coloring based on what they know about the color densities on those specific subcosets.
Ah, so it's like using the counting lemma to zoom in on those subcosets and say, okay, based on the recoloring, if the pattern is still here, it must have been a lot more abundant before.
Precisely. The counting lemma gives them the mathematical framework to make that argument precise. But here's the catch. When they apply the counting lemma to this scenario, it tells them that the density of the pattern under the original coloring would have been much higher than we initially assumed. And this creates a contradiction, a mathematical impossibility.
Huh. It's like the pattern is trying to have its cake and eat it too. It can't be both rare in the original coloring and still present after the recoloring.
Exactly. That contradiction blows their initial assumption right out of the water. The only logical conclusion is that the recoloring they came up with in lemma 5.4 must actually be completely free of the pattern. And that's how they prove theorem 5.5.
Wow, that's pretty elegant, tying it all together like that. And the paper doesn't stop there. They go on to discuss some pretty interesting implications and potential directions for future research. Like, one that really caught my eye was the possibility of extending this result to remove not just one, not just two, but an infinite number of partition-regular patterns. Is that even possible?
It sounds crazy, right? But they make a pretty compelling argument. The idea is to cleverly group these infinitely many patterns into a finite number of super patterns, kind of like prototypes that capture the key features of the whole family of patterns.
Ah, so instead of trying to swat down every single fly, you target the nest.
Exactly. And then, by applying their induced removal lemma, specifically theorem 5.5, to these super patterns, they can effectively eliminate all the individual patterns that fall under their umbrella.
That's incredibly clever.
Yeah.
But I imagine there's still some pretty big hurdles when it comes to extending this approach.
Yeah.
Especially when you're dealing with more complex patterns.
Oh, absolutely. This paper provides a great foundation for dealing with complexity 1 patterns. But going beyond that to patterns defined by multiple equations or even nonlinear equations, well, that's going to require some serious innovation. The authors acknowledge this and point to those challenges as fertile ground for future research.
It's like they've opened this door to a whole new world of mathematical possibilities. But the landscape beyond that door is still largely uncharted. Now, before we wrap up this part of the discussion, I want to circle back to something you mentioned earlier. The connection between this work and the structure of vector spaces. Can you expand on that a bit for our listeners?
Absolutely. While this paper is mainly focused on removing patterns, the techniques and results they present also have implications for our understanding of vector spaces at a fundamental level. For example, Corollary 1.7 highlights a deep connection between the density of a subset and how close it is to being a subspace.
So it's not just about rearranging the furniture, it's about understanding the architecture of the house itself.
Exactly, and it's this interplay between different areas of mathematics that makes this field so fascinating. The tools and insights we develop for one problem can often have unexpected applications in seemingly unrelated areas.
That's a great point. It's a good reminder that mathematics is not just about solving problems in isolation. It's about exploring the connections between ideas and discovering the underlying beauty and elegance that connect them all.
Couldn't have said it better myself. And who knows what other amazing discoveries await us as we continue to explore this incredible world of mathematics.
Indeed. Well, for now, let's take a short break. But when we come back, we'll delve even deeper into the mathematical details of this paper, particularly the role of the counting lemma and its connection to Radau's column conditions. So stay tuned, folks.
It really highlights the power of using the right mathematical tools for the job. By carefully combining things like the arithmetic regularity lemma, Rado's column conditions, that clever subcoset selection strategy, and the counting lemma, they've managed to achieve something really impressive.
It's like they've composed a symphony of mathematical concepts, each one playing a specific role to reach that satisfying conclusion. But before we get too carried away, let's bring it back down to earth for our listeners who have been diligently following along. What are some of the key takeaways from this paper? The big picture stuff, if you will.
Sure. I think the biggest takeaway, the most significant one, is that they've finally achieved complete pattern removal for partition-regular patterns of complexity 1. That's been a tough nut to crack in this field, and this paper provides a really elegant solution.
Absolutely. They've essentially figured out the secret formula, at least for this specific category of patterns. It shows that complete removal is achievable when you have the right tools and the right approach. What would you say is the second most important takeaway?
I'd definitely highlight their innovative subcoset selection strategy. Moving away from the traditional methods by allowing multiple subcosets to be chosen within each partition well, that provides a much-needed flexibility to achieve both regularity and pattern consistency.
It's like they've fine-tuned their recoloring process, making it more precise and effective. It's all about finesse. Any other key takeaways you'd like to mention?
Yeah, I think it's important to emphasize the broader implications of this work, particularly the idea of extending these results to remove an infinite number of patterns and to handle patterns of higher complexities. Those are still open challenges, of course, but this paper lays a really solid foundation for future research.
It's like they've shown a light on the path ahead, even though parts of that path are still shrouded in mystery. But before we wrap up this deep dive, I want to touch on something you mentioned earlier, the connection between this research and the very structure of vector spaces. Can you elaborate on that a bit more for our audience?
Of course. While the main focus of this paper is on induced arithmetic removal, the techniques and results they've presented also have some interesting implications for how we understand vector spaces at a fundamental level. For instance, corollary 1.7 reveals a really intriguing link between the density of a subset and its closeness to being a subspace.
So it's not just about moving the pieces around on the chessboard, it's about understanding the very rules of the game.
Exactly. And that's what makes this field so captivating. The tools and insights we gain by working on one problem can often shed light on other seemingly unrelated areas. It's all connected.
That's a great point. It reminds us that math isn't just about solving problems in isolation. It's about exploring that interconnected web of ideas and finding the hidden elegance and beauty that tie everything together. Now let's get back to the proof of theorem 5.5 and explore some of the mathematical details. I'm particularly interested in the role of the counting lemma and its connection to Rado's column conditions.
Okay, let's revisit the setup. We have a system of linear forms denoted by L that defines our pattern, and we want to demonstrate that if an R coloring has a low density of this pattern, we can find a recoloring that makes it vanish completely. And our primary tool for this is lemma 5.4, which provides us with that special recoloring.
Right, and we're employing a proof by contradiction to show that the recoloring from lemma 5.4 actually achieves this complete pattern removal. That's like a classic detective story.
Oh, got it. The first step is to take our system of linear forms, L, and represent it as a matrix. We can write each linear form in L as a linear combination of variables, and the coefficients in these combinations become the rows of our matrix, which we call ML.
So each row in this matrix represents one of those linear forms in our pattern, and the columns represent the variables we're working with.
Right. Now, the image of this matrix, denoted ML, basically represents all the possible outputs we can get when we multiply ML by any vector. So this image corresponds to all the potential values our linear system L can have as we let those variables run wild across the entire vector space.
It's like a map showing us all the places our pattern could potentially pop up in the vector space.
Exactly. But now we need to consider the linear dependencies between the linear forms in L. These dependencies are captured by something called the kernel of the transpose of ML, which we denote as ker, MLT. The kernel essentially contains all those vectors that, when multiplied by the transpose of ML, give us the zero vector.
So the kernel helps us understand the hidden relationships between the different parts of our pattern. It tells us which combinations of those linear forms will basically cancel each other out and result in zero.
And here's a key insight. The linear dependencies captured in MLT actually correspond to vectors that are orthogonal to the image of ML. In other words, they live in a space that's perpendicular to where our pattern instances reside.
It's like having two separate worlds, the world of our pattern and the world of its dependencies. And they're intimately connected, but they exist in different dimensions. It's a bit mind-bending.
To handle these dependencies, we create another matrix called KL, whose rows are formed by a basis of Ker-MLT. A basis is basically the smallest set of vectors that can span the entire kernel, like a minimal set of building blocks.
So KL is like a condensed version of all those dependencies in our system. It's like a cheat sheet for understanding the pattern's inner workings.
Exactly. And the cool thing is that the solutions to the equation KLZ equals 0, give us precisely the values our linear system L can have as those variables range over the entire vector space. It's like we've found a secret passage to access the world of our pattern by exploring the world of its dependencies.
That's really neat. It's like unlocking a secret code. Now bring back that concept of partition regularity. How does it tie into all of this?
Well, we say that our linear system L is partition regular if and only if this matrix KL we've constructed satisfies what are known as Raddo's column conditions. These conditions basically tell us that we'll always be able to find monochromatic solutions to the equation KLZ no matter how we choose to color our vector space.
It's like having a guarantee that our pattern, in its encoded form as KL, will always leave its mark on the vector space, no matter how much we try to camouflage it with colors.
Right. And here's where theorem 4.2, a quantitative version of Raddo's theorem for finite fields, comes into play. It tells us that if KL meets those Raddo's column conditions, we're not just guaranteed a few monochromatic solutions, we're guaranteed a whole bunch of them. And this abundance is crucial for our proof.
It seems a little strange that we'd want so many instances of the pattern, especially since our goal is to get rid of it entirely.
Yeah, it does seem counterintuitive at first. But remember, we're working with the assumption that the pattern already has a pretty low density under our initial coloring. This large number of solutions actually gives us more wiggle room to carefully select those special subcosets that will disrupt the pattern when we apply our recoloring strategy in lemma 5.4. It's all about strategic disruption.
It's like having a surplus of building blocks that we can rearrange to create a structure where the pattern can't possibly fit in anymore.
Now let's zoom in on lemma 5.3, which is all about finding those special subcosets. This lemma states that given a set of functions, in our case, these are the indicator functions for our different color classes, we can always find a subspace H and a set of vectors Z1 up to Zim that satisfy some very specific properties.
And those properties are what ensure our chosen subcosets will play nice with our coloring and align with the structure of the pattern we're trying to eliminate. It's all about finding the right team players.
Exactly. First, the lemma ensures that our vectors, Z1 through Zim, are solutions to the equation KLZ equals 0, 1. This guarantees our chosen subcosets are compatible with the pattern's underlying structure. It's like making sure our building blocks fit together properly.
It's like making sure our building blocks can actually connect to form the structure we need to break down.
Second, the lemma guarantees that each subcoset H plus Zj is regular with respect to our coloring. Remember, regularity essentially means our coloring behaves predictably on these subcosets, no wild fluctuations in color densities.
It's like having a nice, smooth terrain where we can confidently execute our recoloring strategy.
And third, the lemma ensures that for each color, either all of our chosen subcosets have a low density of that color, or they all have a high density. This is crucial for disrupting that pattern when we recolor.
It's like making sure our building blocks either all lack a certain type of connection or all have it in abundance, no in between.
Exactly. Now, to prove lemma 5.3, we use the arithmetic regularity lemma to find a subspace H that divides our vector space into mostly regular cosets. Then we introduce an auxiliary coloring on the set of all possible cosets of H. This auxiliary coloring basically encodes information about which color densities are high and which are low on each coset. And finally, we apply Raddo's theorem to this auxiliary coloring to find a set of cosets that tick all the boxes for lemma 5.3.
So we're basically using the arithmetic regularity lemma and Raddo's theorem to set the stage and carefully pick these special subcosets. It's like setting the trap before we spring it.
Precisely. Now, to apply lemma 5.3 to our original coloring, we represent each color class as an indicator function. This lets us translate our colorful picture into a more abstract mathematical language that we can manipulate using the tools we've developed. And that brings us to lemma 5.4, which combines all these elements to construct our recoloring card. It's like the grand finale of our mathematical symphony.
Right. Lemma 5.4 is where all the pieces come together.
Yeah.
Can you walk us through how this lemma actually builds that recoloring?
It starts by applying the arithmetic regularity lemma, much like we did in the proof of lemma 5.3, to find a series of nested subspaces. This creates a multi-layered structure of well-behaved cosets that will guide our recoloring.
It's like laying down a strong, multi-layered foundation for our new structure, making sure each layer is stable and predictable. No shaky foundations here.
Then we use lemma 5.3 on that innermost subspace to find a set of subcosets that are both regular and compatible with the structure of our pattern. These subcosets will act as representatives for their corresponding cosets in the coarser partition. They're like delegates, representing the interests of their regions.
Each delegate has a voice.
Now comes the recoloring itself. For each coset in that coarser partition, we look at the color densities on its representative subcoset. If a color is rare on the representative subcoset, we recolor all instances of that color within the entire coset to a color that's more common. That's the key move to disrupt the pattern from forming.
It's like evening out the playing field within each region to achieve harmony across the board, at least in terms of color distribution.
The lemma carefully chooses parameters to ensure that this recoloring only changes a small portion of the vector space. And the resulting recoloring has a very interesting property. If you see a color at least once in a coset under her, it means that color was quite common on the representative subcoset under our original coloring. So every color that survives in this new structure had a strong base of support from the beginning.
So every color that makes it into the final structure had strong support from the ground up. Democracy in action. How does this property help us prove that Quark is actually pattern-free?
That's where the counting lemma shines. Remember, we're operating under the assumption that our pattern starts with a low density under the original coloring. But if we did find a sneaky instance of the pattern lurking in the recolored space under Hoare, we can use the counting lemma and the special property of Hoare to show that the pattern must have had a much higher density under her than we originally thought. It's like using the evidence left behind to reconstruct the crime scene.
The counting lemma is our mathematical detective. It uses the clues left behind by the recoloring to reveal the pattern's true prevalence in the past.
Exactly. And that leads us to a contradiction, which ultimately proves theorem 5.5. It's like the pattern tripped over its own footprints, revealing its guilt.
This has been a truly fascinating deep dive into induced arithmetic removal.
Yeah.
It's definitely a lot to take in, but the elegance of their approach and the potential implications are truly exciting.
It's truly a testament to the power of thoughtful mathematical construction and the beauty of connecting seemingly disparate ideas to achieve something remarkable. And I'm sure there are many more exciting discoveries waiting to be uncovered in this field.
Absolutely. And to our listeners, we encourage you to explore this paper further and see what insights you can glean from it. Who knows, you might even be inspired to make your own contributions to this fascinating area of mathematics. Until next time, keep those mathematical minds sharp and never stop exploring the wonders of the mathematical universe.
Yeah, it really shows you what you can accomplish when you carefully select and combine the right mathematical tools. They've taken the arithmetic regularity lemma, Roddo's column conditions, that clever subcoset selection strategy, and the counting lemma, and blended them together to create something truly remarkable.
It's like they've orchestrated a symphony of mathematical concepts, each playing its part to bring us to that satisfying conclusion. But let's not forget about our listeners who have been patiently following along with all these intricate details. Before we wrap things up, maybe we could distill the essence of this paper into a few key takeaways for them. What would you say are the most important things to remember from this deep dive?
For me, the most significant takeaway is that they've finally cracked the code on complete pattern removal for partition-regular patterns of complexity 1. That's been a long-standing puzzle in this field, and this paper presents a really elegant solution.
It's a big deal. They've shown that with the right tools and approach, complete removal is actually achievable for this specific family of patterns. What would you say is the second most important takeaway?
I'd highlight their innovative subcoset selection strategy. It's a clever departure from the traditional methods. By allowing for the selection of multiple subcosets within each partition, they introduce a crucial level of flexibility that's needed to achieve both regularity and pattern consistency. It's like they found a way to fine-tune the recoloring process to make it even more precise and effective.
It's all about finesse. Any other key takeaways you'd like to mention?
I think it's important to remember the broader implications of this work. There's the potential for extending these results to remove an infinite number of patterns, imagine that, and also the challenge of tackling patterns of higher complexities. Those are still open problems, ripe for exploration, but this paper provides a solid foundation for future research in those directions.
It's like they've opened a door to a whole new world of mathematical possibilities, even though the landscape beyond that door is still largely unexplored. But before we conclude this deep dive, I want to revisit something you mentioned earlier, the connection between this work and the structure of vector spaces. Can you elaborate on that a bit more for our listeners? What does this research tell us about the fundamental nature of these mathematical objects?
Certainly. While the primary focus of this paper is on induced arithmetic removal, the techniques and results they present also have some profound implications for our understanding of vector spaces. For example, Corollary 1.7 uncovers a deep connection between the density of a subset and how close that subset is to being a subspace.
So it's not just about rearranging the pieces on the chessboard. It's about gaining a deeper understanding of the rules of the game itself.
Exactly. And that's one of the things that makes this area of mathematics so fascinating. The tools and insights we develop for one problem can often have unexpected and profound applications in seemingly unrelated areas. It's a testament to the interconnectedness of mathematical ideas.
That's a great point to end on. It reminds us that mathematics is not just about solving isolated problems. It's about exploring the intricate web of ideas and discovering the underlying beauty and elegance that connects them all.
Well said. And who knows what other fascinating discoveries await us as we continue to explore this incredible world of mathematics.
Indeed. And to our listeners, we encourage you to delve deeper into this paper and see what other insights you can uncover. Perhaps you'll even be inspired to contribute to this exciting field of research. Until next time, keep those mathematical minds sharp and never stop exploring the wonders of the mathematical universe. Welcome to the Deep Dive. Today we're diving into some pretty cool math research called Induced Arithmetic Removal. We're going to be looking at how certain patterns, especially in things called vector spaces over finite fields, can be made to just disappear. It's kind of like we're taking this complex mathematical structure, and by recoloring it, we can make those patterns vanish. Our main source for this deep dive is V. Gladkova's paper, Induced Arithmetic Removal for Partition-Regular Patterns of Complexity 1.
That's a great analogy. The paper really delves into a specific type of pattern, those partition-regular patterns of complexity 1. They have a special property that makes them really interesting for induced removal.
Now, before we get too into the weeds with this paper, can we just take a step back for a second, talk about arithmetic patterns in general? I know our listeners are pretty familiar with the basics, but just to set the stage.
Yeah, absolutely. So when we talk about arithmetic patterns in vector spaces over finite fields, we're essentially talking about solutions to systems of linear equations. You can think of each equation in the system as having a specific color. And then a solution to the system where each equation satisfies its assigned color represents an instance of an arithmetic pattern.
So it's like a colorful system of equations. The colors add this whole other layer of complexity.
Exactly. A simple example is a monochromatic three-term arithmetic progression. So if we have a pattern, let's say xx plus d, x plus 2, and we're working with a two-coloring, we'd have two instances of this pattern. One where all three terms are, say, red, and another where they're all blue.
Okay, that makes sense. Now, where do these induced removal lemmas come in? What are they trying to do with all this?
Well, they're like instructions for how to recolor the vector space strategically to try to, well, minimize or even completely eliminate the occurrences of the specific arithmetic patterns.
So they're kind of like a guide for recoloring the space so that certain patterns, poof, disappear.
Precisely. But there's a catch. Previous induced removal lemmas, they're a little limited. They could only guarantee the removal of almost all instances of a pattern. There were always these almost like leftover bits, non-generic remnants that just wouldn't go away no matter how you tried to recolor the space.
Ah, so that's where Gladkova's work steps in. This paper finds a way to actually get rid of those patterns completely in certain cases.
Right, that's the breakthrough. Gladkova specifically focuses on partition-regular patterns of complexity 1 and shows that for these types of patterns, you can actually achieve complete removal. It's pretty big.
Before we jump into the specifics of that, can you tell us what's so special about these partition-regular patterns? What makes them stand out?
Sure. So a partition-regular pattern, it's kind of cool. It always guarantees you're going to have at least one instance where all the elements are the same color. No matter how you color the vector space, you're stuck with at least one instance of this monochromatic solution. Gladkova gives a formal definition for this in the paper Definition 1.3. It spells it out in the context of vector spaces over finite fields.
So no matter how you try to hide these patterns with different colors, There's always going to be at least one instance where they're all the same color.
Exactly. And that's a crucial property. Gladkova uses that to prove theorem 1.5.
Can you walk us through the highlights of that theorem? What's the main takeaway there?
Theorem 1.5, that's the heart of the paper. It basically says that for partition-regular patterns of complexity 1, you can completely remove all instances of the pattern just by recoloring a small part of the vector space. This is a huge step forward from previous work, which, remember, could only get rid of almost all instances.
That's a pretty big difference. Is there an example that shows how this works in action?
Gladkova gives a great example, example 1.6. Imagine you have a vector space over a finite field, and you've colored it with 4 colors, right? We're looking at solutions to this equation, x plus y plus zw equals 0 night. But here's the thing. Each variable needs to have a different color. We call that a rainbow solution. Now, with the old methods, you could only remove those solutions where none of the variables were 0. But with theorem 1.5, you can get rid of all the rainbow solutions, even the ones that include 0. It's much stronger.
So it's a much more powerful result than what we had before.
Definitely. And it comes down to this clever new strategy that Gladkova uses for picking subcosets within the vector space.
Okay, now I'm really interested. Can you tell us more about this new subcoset selection strategy? What's the main idea?
The trick is to choose multiple subcosets as representatives, kind of like picking multiple delegates within each coset of a bigger partition. The older methods, they usually just pick one subcoset from each coset.
So instead of one rep per coset, now we have a whole team of reps.
That's a great way to think about it. And having this team, it gives you so much more flexibility, and control when you're trying to change the coloring of the space.
I see how that could be a game changer. How do you pick these reps, and how does that help us eliminate those patterns?
The selection process is key. Each of those subcosets, they have to meet certain criteria. First, it has to be regular, meaning the colors inside that subcoset are kind of mixed up in a random way. This is important because it lets us use this thing called the counting lemma, which helps us figure out how many times the pattern shows up.
Hold on, I think we talked about that counting lemma a bit in part 1. Can you remind me what it does again?
Of course. The counting lemma, it's specifically lemma 2.7 in the paper. It's basically a tool to estimate how many times you'll see a linear system within specific parts of a subspace, these things called cosets. It tells you how many solutions you can expect to find, but only if the cosets meet certain conditions, like being regular, which we just talked about, and consistent with the pattern, which we'll get to.
Okay, so regularity is one of the things we need for picking our subcoset reps. What's the other one?
The second criteria is consistency. It means that if a bunch of cosets could potentially have the pattern inside them, then the reps we choose from those cosets, they should also be able to form an instance of the pattern. It's like making sure they can actually represent what's happening with the pattern in those cosets.
So we're making sure our reps are kind of qualified to represent the pattern, right?
Exactly. And by being super careful about how we choose these reps based on regularity and consistency, we can then change the coloring in a very specific way that leads to getting rid of the entire pattern. It's pretty awesome.
This is fascinating. It's like building this complex machine with all these carefully chosen parts.
I like that analogy. It really captures the essence of Gladkova's approach. And to really understand how it all works, we need to look at the proof of theorem 1.5 in more detail.
That sounds like a great starting point for part 2 of our deep dive. We'll break down the proof step by step and see how all these concepts we've been discussing actually come together to achieve this remarkable result. Stay tuned. Welcome back to the deep dive. In part 1, we laid the groundwork for our exploration of induced arithmetic removal, zeroing in on Gladkova's groundbreaking work on getting rid of partition-regular patterns of complexity 1. Now let's get our hands dirty and dig into the proof of theorem 1.5. It's the core of this whole paper.
Yeah, I'm excited to break this proof down. It's really a beautiful example of how different concepts come together.
So where do we even start? What's the overall game plan for this proof?
Well, it starts by setting up the problem, right? We're given this arc coloring of a vector space.
Right.
Basically, every element has one of our different colors. Our mission is to recolor just a small part of it to wipe out all instances of that partition-regular pattern we're after.
So it's like we're starting with this colorful mess, and we have to strategically repaint some parts of it to make those patterns disappear.
Exactly. The first move is using this thing called the strong arithmetic regularity lemma. It's super powerful in this area of math. It lets us take the vector space, which seems all chaotic and jumbled up, and break it down into a much more organized structure.
Oh yeah, the regularity lemma. It's like sorting a bunch of random stuff into labeled boxes. It gives us a way to understand how the colors are spread out in these boxes, or cosets as they're called.
Right. It's like organizing our collection of colored elements into boxes based on how they behave. And then the regularity lemma helps us analyze how the colors are spread out in each gusset.
Okay, so we've used the regularity lemma to tidy up the chaos. What happens next?
This is where Gladkova's innovation comes in, this multi-subcoset selection strategy. Inside each of these organized cosets, we got to carefully pick out a group of subcosets to be like representatives, like picking the best delegates from each box to speak for the whole coset.
Yeah, and we talked about those representatives needing to be regular and consistent. Can you refresh my memory on what that means again?
Sure. Regularity means that the subcosets we pick should have a good mix of colors, like they're pretty randomly distributed within that subcoset. That's important for using the counting lemma properly.
Oh yeah, the counting lemma. That's what we use to estimate how many times that target pattern shows up. Regularity makes sure we're counting things right. But what about consistency?
Consistency basically means our reps accurately reflect what's happening with the pattern in the whole coset. So if a group of cosets could potentially contain an instance of our pattern, the reps we choose from those cosets, they got to be able to form an instance of the pattern too.
So consistency is like making sure our reps aren't lying to us about what's going on in the coset. They're like true representatives of the pattern's behavior.
Exactly. And the really cool thing is, with partition-regular patterns, we're guaranteed to find reps that are both regular and consistent. That's because partition-regular patterns always have these monochromatic solutions no matter what.
Okay, I see how that special property of partition-regular patterns comes in handy here. So we've got our awesome reps, they're ready to go. Now it's time for the recoloring, right?
Right. Recoloring is pretty straightforward, actually. We look at each representative subcoset, and for each color, we see how often it shows up, like its density. If a color isn't showing up enough, if its density is low, we essentially erase it from the corresponding coset and swap it out with a color that's got high density in that rep.
It's a popularity contest. Only the colors that are popular get to stay.
Haha. Yeah, that's a good way to put it. And this simple recoloring trick leads to some pretty cool results. Remember how we made sure our reps were consistent with the pattern? That means if an instance of the pattern survives our recoloring rampage, it has to have a twin, like a potential instance, hanging out in the chosen reps as well.
Oh, right, because our reps were like little mini-me versions of the cosets, showing us what the pattern was doing in there. So if any part of the pattern survives, it's got to have a buddy in the reps.
You got it. But here's the catch. We only kept the most popular colors in each rep, right? So any color that's still hanging around in a surviving instance of the pattern, it must have been really popular in at least one of its reps.
It's like a trap. We made those colors be popular in the reps, so now they can't hide.
Exactly. And this is where the counting lemma swoops in to save the day. Remember, regularity lets us use the counting lemma, right? So if a color is in a surviving instance of the pattern and it was popular in one of its representative subcosets, well, the counting lemma says there must have been a ton of instances of that pattern in the original coloring, like way more than we thought there were at the beginning.
Wait, so by forcing those colors to be popular in the reps, we accidentally created a situation where if any part of the pattern survives, it just doesn't make sense anymore?
Bingo. That contradiction, that's the heart of the proof. It means that after we do our clever recoloring, there can't be any instances of the pattern left. Poof, gone. Complete removal.
Welcome back to the deep dive. We've spent the last two parts really digging into this idea of induced arithmetic removal, and we've seen how Gladkova came up with this incredible proof for totally wiping out partition-regular patterns, the ones with complexity 1. Now that we've got our heads around the nitty-gritty of the proof, I want to zoom out a bit. What's the big picture here?
I'm glad you asked that. It's super important to see how these technical details connect to the broader implications. What does this tell us about these structures, these mathematical structures we've been talking about, and where do we go from here? What other questions can we ask now?
Exactly. What doors does this open up for us? We talked about tower-type bounds and Wowzer functions earlier. Can you remind me what those were all about? What do they mean for actually using this technique?
Sure. So those terms, they're all about how complex this process gets as the patterns we're dealing with get more and more complicated. Tower-type bounds, they tell us how quickly the resources we need to do this recoloring blow up as the problem gets bigger. It's like you're trying to solve a giant puzzle, and as it gets bigger, you need way more pieces and way more time to solve it.
So basically, the more complex the pattern, the harder it is to get rid of it, like computationally.
Exactly. And those Wowzer functions, they represent an even crazier type of bound, showing just how complicated the tools we're using really are. Especially those regularity lemmas, they're powerful, but they come with a cost. It's a balancing act between being accurate and being efficient.
So even though Gladkova's proof is awesome because it guarantees we can completely get rid of these patterns, actually doing it in the real world could be really difficult if the patterns are super complicated.
That's right. But that's kind of how it is with these groundbreaking math discoveries, you know? They lay the foundation, and then the next step is figuring out how to make them work better in practice.
Are there any ways we could make these techniques more efficient?
Absolutely. In fact, Gladkova mentions some really promising research by Manners in the paper. Manners showed that the bounds for something called true complexity can be, well, polynomial. That suggests there might be other ways to approach this, ways to make these algorithms more practical.
So there's hope for taming those Wowzer functions and making these techniques actually usable.
Oh, definitely. It's a really active area of research right now. Figuring out how to bridge the gap between those beautiful theoretical results and actually using them, that's what pushes math forward.
It's kind of wild how, even in this abstract world of math, we still have to deal with real-world limits, like how much computing power we have.
It is. It's a constant back and forth between the theoretical and the practical. So, switching gears a little bit, I'm also curious about taking Gladkova's work further. Like, right now, the proof is all about partition-regular patterns of complexity, one in finite fields. Could we use similar ideas for more complex patterns, or maybe even in different mathematical settings?
That's a great question. It's like we've climbed this one mountain, and now we're looking at a whole range of peaks and wondering which one to try next. What kind of challenges would we face trying to climb those other peaks?
One of the big ones is wrapping our heads around higher-order Fourier analysis. That's what we use to analyze these more complex patterns. Gladkova's proof uses the standard Fourier transform, and that works great here. But when you try to go to higher-order Fourier analysis, things get, well, a lot messier, and we just don't understand it as well yet.
So we need, like, better tools and maps to explore this more complicated mathematical territory.
Exactly. Another challenge is figuring out how to apply the idea of partition regularity itself to other types of structures. Finite fields, they're structured in a specific way that makes partition regularity work really nicely. But in other settings, it might not be so simple.
It's like we're trying to translate from one language to another, but the grammar and the words don't line up perfectly. We need to really get those underlying structures to figure out how to make partition regularity make sense in those new contexts.
I love that analogy. It really gets at the core of the problem. But even though there are these challenges, figuring it out would be huge. If we can generalize these techniques, we'd have these amazing new tools for understanding all sorts of mathematical structures.
That's exciting. What could we do with those tools? Like, what kind of applications are we talking about?
Oh, the possibilities are endless. It could impact theoretical computer science, cryptography, even physics. Like, in computer science, imagine designing algorithms that are way more efficient for finding or avoiding patterns. That's just one example.
So these abstract math ideas, they could actually change how we build and analyze algorithms in the real world.
Absolutely. And in cryptography, think about new ways to make encryption even stronger so that hackers can't break the codes by finding patterns in the data.
It's amazing how research in this really abstract part of math could end up having effects in so many different areas.
I know, right? It just goes to show how interconnected everything is. These ideas that seem so out there can lead to some pretty incredible advancements.
This deep dive into induced arithmetic removal has been a wild ride. We started with this simple idea like making patterns vanish, and we ended up exploring these crazy, complicated proofs, powerful mathematical tools, and a whole universe of unanswered questions.
It's been a blast exploring this with you. I hope everyone listening has a better appreciation for just how cool and deep math can be. Even the most abstract stuff can have a real impact.
I know I do. It's a good reminder that math isn't just about getting the right answer. It's about asking the right questions and, being okay with not knowing everything and always trying to push the limits of what we understand.
Well said. Who knows what we'll find out there?
That's the best part. There's always something new to discover in math. Thanks for joining us on this deep dive into induced arithmetic removal. Keep those math brains working, and we'll see you next time. Welcome to today's deep dive. where we'll be exploring induced arithmetic removal in mathematics.
Oh, this is a fascinating area.
Yeah, it really is. I've always been intrigued by how it kind of combines ideas from graph theory and combinatorics, but then applies them in a completely different setting, like vector spaces over finite fields.
Yeah, it's like taking that familiar idea of removing subgraphs to disrupt a network.
Right.
But instead of edges and vertices, we're dealing with vectors and these arithmetic patterns.
It's almost like we're performing surgery on this mathematical structure, trying to precisely remove a pattern without messing up the whole space.
That's a great way to put it. And one of the things that makes this problem particularly interesting is that complete removal. Getting rid of every single instance of a pattern isn't always possible.
Yeah, some patterns are just so deeply embedded.
Exactly. It's like they're woven into the very fabric of the vector space.
It's like trying to remove a load-bearing wall. Yeah. Sometimes the structure just can't handle it.
Perfect analogy. And the key to understanding whether a pattern can be completely removed is this concept of partition regularity.
Okay, partition regularity.
It's really at the heart of the paper we're discussing today.
So what exactly does that mean?
Well, a pattern is considered partition regular if no matter how you color the elements of the vector space, you're guaranteed to find at least one instance of that pattern where all the elements have the same color.
Oh, I see. So it's like saying no matter how you try to divide up the vector space with different colors, this pattern will always find a way to express itself.
Exactly. It's like a mathematical chameleon that can blend into any coloring scheme we throw at it.
Okay, that's a cool way to think about it. So if a pattern is not partition regular,
then things get a bit trickier.
Okay, why is that?
Well, let's look at example 1.4 from the paper to illustrate this.
Okay.
Suppose we have a matrix A over a finite field, and this matrix is not partition regular.
Right.
This means there's some coloring where the only solution to the equation AXX is the zero vector itself.
And we can't change that, right?
Exactly. No amount of recoloring is going to change the fact that the zero vector is always going to be the zero vector.
I mean, it's like an anchor point.
Precisely. It's an inherent property of the vector space.
Okay, so even if we try to be clever with our recoloring, that one instance of the pattern is going to stick around.
Yeah, making complete removal impossible.
Okay, I'm starting to see why this partition regularity is so important. It's like the dividing line between patterns we can completely get rid of and those that we can't.
That's a great way to summarize it.
So this paper focuses specifically on induced removal for those special partition regular patterns, right?
Yes, and to be even more precise, it focuses on patterns of complexity 1.
Complexity 1.
A classic example is the three-term arithmetic progression, where each term is just the previous term plus some constant difference.
Right, it's like a fundamental building block of arithmetic.
Exactly, and this pattern pops up all over mathematics, from number theory to computer science.
Okay, so it's a pretty important pattern to understand. Now, I understand that this paper builds on previous work in this area, specifically Theorem 1.2 from Fox-Tidor and Zhao.
Yes, that's right.
Can you remind us what that theorem achieved?
Of course. So Theorem 1.2 showed that induced removal was possible for a wide class of patterns, but there was a catch. It could only guarantee removal for almost all instances.
Almost all?
Yeah. There could be some stubborn cases, particularly those involving the zero vector, that just wouldn't budge. It's like clearing a field of weeds, but finding a few stubborn roots that just won't come out.
Ah, so close, but not quite complete solution.
Right. And that's where our paper comes in.
Okay.
So Theorem 1.5.
Theorem 1.5.
It says, hey, even for those trickier partition regular patterns, we can actually achieve complete removal.
Wow, that's pretty exciting.
It is, and the key to this complete removal is a new strategy for selecting subspaces within the vector space.
Subspaces, okay.
Think of it as a refined, more powerful version of what Fox-Tidor and Zhao did, but with a crucial twist.
Okay, I'm definitely hooked. Tell us more about this new strategy. What's the secret sauce here?
Instead of choosing a single subspace as a representative, we carefully select multiple subspaces within each coset of a coarser partition.
Okay, multiple subspaces.
Imagine we have this initial division of our vector space into these larger cosets. It's kind of like dividing a cake into slices.
Okay, I'm visualizing the
cake. And then within each slice, we choose several smaller pieces.
Smaller pieces, got it.
Each representing a different subspace, this gives us a lot more flexibility when we define our recoloring.
Oh, I see. So it's like having a team of representatives instead of just one, giving us more options to work with.
Exactly. And this is really what allows us to achieve that complete removal even for those more challenging instances.
Okay. I'm really eager to see how this works in practice. Can you walk us through an example?
Absolutely. Let's dive into the details. So we left off talking about selecting multiple subspaces instead of just one, and how that gives us more flexibility.
Yeah, it definitely sounds promising, but I'm still having a little trouble wrapping my head around how this all works in practice.
I understand it can seem abstract at first. How about we look at a concrete example to make it more clear?
Oh, yeah, that'd be great.
Okay, so let's turn to example 1.6 from the paper.
Yeah.
It deals with removing rainbow solutions.
Rainbow solutions, what are those?
Imagine we're working with a four-coloring of our vector space.
Okay, 4 colors.
Our goal is to eliminate all instances where the equation x plus y plus 0 equals 0.
Okay, x plus y plus zw is 0.
Has a solution where all 4 variables, x, y, z, and w, are all different colors.
Oh, I see. So it's like finding those special sets of 4 elements where each one represents a different color, and they all satisfy that equation.
Exactly. It's like trying to find a perfectly diverse quartet that sums up in just the right way.
And then we make them disappear.
Precisely. Now, the key point here is that this specific pattern, the rainbow solution, is partition-regular.
Ah, so it falls under the umbrella of what we can work with.
Yes, which means no matter how we color the vector space, we're guaranteed to find at least one of these rainbow solutions.
Okay, so theorem 1.5 should apply here, right?
You got it. Theorem 1.5 tells us we can actually eliminate all these rainbow solutions just by recoloring a tiny fraction of the vector space.
It's like we have this mathematical magic wand that can make specific patterns disappear.
That's a great way to think about it, and the paper gives a specific scenario to illustrate how this might work.
Okay, what's the scenario?
Let's say one of our 4-color classes,
okay,
let's just call it color 1, is significantly smaller than the others.
All right, so one color is kind of underrepresented.
Exactly. It's like having a bag of marbles where one color is a lot less common than the rest.
I could see that.
Because this color 1 is less common, there are going to be relatively few instances of our rainbow pattern to begin with.
Okay, why is that?
Well, most potential solutions are going to have at least 2 elements with the same color, right?
Right, because color 1 is rare.
So they wouldn't qualify as rainbow solutions.
Oh, I see. So the scarcity of color 1 is already limiting the number of rainbow solutions we need to worry about.
Precisely. And theorem 1.5 tells us that if the number of those rainbow solutions is below a certain threshold, we can eliminate all of them by just recoloring a tiny epsilon proportion of the vector space.
Epsilon, that's our way of saying a really small amount.
Yeah, exactly. And remember, epsilon can be made arbitrarily small.
So we're talking about very minor changes.
Right. We just tweak the coloring of a tiny portion of the space and poof, those rainbow solutions are gone.
Okay, that's pretty amazing. But in this specific case, wouldn't a simpler approach work?
Oh, what do you have in mind?
Couldn't we just recolor all the elements that have color one with one of the other more common colors?
You're absolutely right. In this particular scenario, a simply recoloring strategy would work.
Okay, so why do we need theorem 1.5 then?
Well, the power of theorem 1.5 is that it's not limited to this specific example. It provides a framework for tackling any partition-regular pattern of complexity.
So it's like having a master key that can unlock a whole variety of mathematical doors.
Exactly. And it's also worth noting that previous approaches, like the one from Fox, Tidor, and Zhao, wouldn't guarantee complete removal in this case.
Oh, why not?
They might leave behind some of those pesky rainbow solutions that involve the 0 vector. Remember those stubborn roots we talked about?
Yeah, those days.
Our new approach with the multi-subcoset selection is more robust. It can handle even those tricky instances.
It's like it goes the extra mile to make sure everything is truly gone.
Precisely. Now that we've seen an example, let's shift gears a bit and dive into how this multi-subcoset strategy is actually implemented.
All right, let's get into the nitty-gritty.
Section 3 of the paper gives a really good overview of this process. It's like a roadmap for how we actually construct the recoloring.
Okay, so what are the key steps involved?
The core idea is to build what's called a regular model.
A regular model. Interesting. What is that?
It's a simplified representation of our vector space that captures the important information about the coloring and the pattern we want to remove.
So it's like creating a blueprint that highlights the key structural elements.
That's a fantastic way to put it. You see, a partition is going to be regular.
Right, some might be a bit messy.
Exactly. But by carefully selecting these representative subcosets, we can create this regular model where almost every coset is well-behaved, meaning it has that nice uniform color distribution.
So it's like we're replacing the messy reality with a more organized and idealized model.
Precisely. And if you want to get a really clear visual understanding of this, I highly recommend checking out the figures provided in the paper, figures 1, 2, and 3.
Oh, those are always helpful. I'm a visual learner.
They do a great job of illustrating how this regular model is constructed step by step.
Awesome. I'll definitely check those out.
Now, after we've laid out the blueprint with the regular model, the paper gets into the more technical details starting in section 5.
Okay, let's get into the weeds.
This is where we see all those lemmas, theorems, and proofs that make this whole strategy work.
I'm ready for it.
One of the key lemmas in this section is lemma 5.3.
Okay, lemma 5.3.
It focuses on selecting those multiple subcosets within each coset of H1. Remember those subcosets that have to satisfy those 3 criteria?
Right, regularity, density, approximation, and pattern consistency.
Exactly, and lemma 5.3 uses a powerful theorem called Rado's theorem over finite fields to accomplish this.
Rado's theorem, okay, I'm not familiar with that one.
It's a really important result in Ramsey theory, and in our context, it basically guarantees that if we have a partition-regular matrix, we're going to find lots of monochromatic solutions to the corresponding system of equations.
Monochromatic solutions. So all the variables in the solution have the same color.
Precisely. Now here's how we apply Rado's theorem to our subcoset selection problem.
Okay, I'm listening.
We introduce what's called an auxiliary coloring on the set of all subcosets.
An auxiliary coloring. So it's like a temporary coloring that we're using for this specific purpose.
Exactly. And this auxiliary coloring encodes those 3 properties we're looking for: the regularity, the density approximation, and the consistency.
It's like we're using this auxiliary coloring as a filter to highlight the subcosets that meet our needs.
That's a great way to think about it. And because our matrix is partition-regular, Rado's theorem guarantees that we're going to find many monochromatic solutions to this auxiliary coloring.
Oh, I see. And each solution represents a set of subcosets that meet our criteria.
Exactly. It's like casting a net and pulling in a whole bunch of perfectly suitable subcosets.
Okay, that's pretty clever.
Now, once we have these carefully chosen subcosets, lemma 5.4 steps in to actually define the recoloring.
Right. We need to use those subcosets to guide how we change the colors.
Exactly. And the goal is to eliminate colors that are rare within those subcosets and replace them on the corresponding coset of H1.
So we're using the smaller groups to inform our changes to the larger group.
Precisely. And lemma 5.4 does this very carefully, making sure that we only change a small epsilon proportion of the entire vector space.
We want to keep our modifications as minimal as possible, right?
Exactly. It's all about precision.
Okay, so we've selected the subcosets and defined the recoloring. What's next?
Now comes the grand finale, the proof of theorem 5.5.
This is where we show that the pattern is actually gone, right?
Exactly. And the proof relies on a classic technique in mathematics, proof by contradiction.
Proof by contradiction. All right. How did that work here?
We start by assuming that an instance of the pattern does exist under our new coloring.
So we're assuming our plan didn't work.
Right, and then we see where that assumption leads us.
Okay, so we're setting a trap.
Exactly. Now remember that our subcosets were chosen to preserve consistency with the pattern.
Right, that was one of our key criteria.
Which means if we have an instance of the pattern in our recolored vector space, we must also have a corresponding instance within those representative subcosets.
So by assuming the pattern survived, we're forcing it to show up in those subcosets as well.
Precisely, and that's where the contradiction comes in.
Okay, how so?
We can now apply the counting lemma, remember our mathematical magnifying glass?
Yeah, it helps us find those hidden patterns.
Since those subcosets are regular and consistent with the pattern, the counting lemma tells us that there should be many instances of the pattern within those subcosets under the original coloring.
So if we see even one instance, there must be a whole bunch more hiding there.
Exactly, but here's the problem. Remember, we constructed our recoloring to eliminate colors that were rare within those subcosets.
Right, we wanted to get rid of those uncommon colors.
So if a color survives in our new coloring, it means it must have been relatively common in at least one of those subcosets.
Wait a minute, so the counting lemma says the pattern should be abundant in those subcosets, but at the same time we're saying the colors that make up the pattern were uncommon there.
That's the contradiction.
It's like saying a book is full of words that don't appear in its pages.
Exactly. It just doesn't make sense. And this contradiction can only mean one thing.
Our recoloring worked.
Precisely. It completely eliminates the pattern.
This is amazing. We've created this incredibly clever trap using those carefully selected subcosets, and it forces the pattern to disappear.
It's a beautiful example of how mathematical logic can be used to achieve surprising results.
I'm completely blown away by this, and to think we're just scratching the surface here.
Right. There's still so much more to explore in this area.
Wow, I'm still reeling from that proof by contradiction.
It's definitely a powerful technique.
It is. But now I'm kind of curious with the bigger picture. Like, where does this all fit into the grand scheme of mathematics?
That's a great question. This paper is a significant step forward in our understanding of induced removal lemmas.
Okay, how so?
Well, it shows that complete removal, which was once thought to be impossible for certain patterns, can actually be achieved for a wider class of patterns than we previously thought.
So we're expanding the boundaries of what's possible.
Exactly, and this has the potential to impact other areas of math, like additive combinatorics, number theory, even computer science.
Whoa, those are some big fields. How could this work influence research in those areas?
Well, let's start with additive combinatorics. This field is all about understanding the structure and behavior of sets under arithmetic operations,
Like addition and multiplication.
Right. And this result by showing that certain patterns can be completely eliminated with just minor modifications.
Okay.
It gives us a deeper understanding of how these arithmetic structures behave within sets.
It's like we have a more powerful tool for analyzing those structures.
Exactly. And it could lead to new insights and techniques for tackling some of the big open problems in the field. Problems related to some sets, densities, things like that.
So it's not just a theoretical result. It could have practical implications.
Absolutely. Now let's move on to number theory.
Number theory, one of my favorites.
It's a fascinating field, and one of its central mysteries is the distribution of prime numbers.
Prime numbers, those elusive building blocks of all the integers.
Right. They seem to follow a pattern, but it's incredibly hard to pin down.
Yeah, it's like they're playing hide and seek with us.
Yeah. Exactly, and this is where our work could potentially offer a new perspective. You see, prime numbers can be viewed as a type of arithmetic pattern, albeit a very irregular one.
Okay, so we could apply some of these ideas about pattern removal to prime numbers.
Potentially understanding how to manipulate and remove patterns within sets might give us new tools for analyzing how primes behave.
It's like trying to study the movement of a flock of birds by seeing how removing individuals affects the overall formation.
That's a great analogy. It's amazing how different areas of math can connect in unexpected ways.
Yeah, it really is. Now, what about computer science? How could this research be applied there?
Well, this work could have implications for things like property testing and algorithm design, especially when dealing with large data sets.
Okay, so more practical applications.
Imagine you have a huge data set, and you need to figure out if it has certain properties related to arithmetic patterns.
Okay.
This work could give us insights into designing algorithms that can test for and potentially modify those properties efficiently.
So it's like taking these abstract mathematical concepts and turning them into real-world tools.
Exactly. It's a great example of how math can be both beautiful and useful.
This has been such an eye-opening deep dive, but I know there's always more to explore. What are some of the open questions that are still out there?
One of the big ones is whether these techniques can be extended to patterns of higher complexity.
Higher complexity, so more intricate patterns.
Right. This paper focused on patterns of complexity. One, like those 3-term arithmetic progressions.
Right.
But what about 4-term progressions or even more complex configurations?
It's like we've figured out how to remove individual weeds, but now we need to tackle entire fields.
That's a perfect analogy, and the paper actually touches on this challenge in section 6.
Okay, what does it say?
It points out that it's really hard to find good analogs to lemma 5.3 for these higher complexity patterns.
That lemma was key for selecting those well-behaved subcosets, right?
Exactly. And without it, our whole strategy kind of falls apart.
So we need a more powerful version of lemma 5.3, or maybe a completely new approach.
It's a tough problem, but it's definitely worth exploring.
It's exciting to think about the potential breakthroughs that might be waiting out there.
Definitely. No, another open question that I find really interesting is whether there are fundamental limits to these induced removal techniques.
Limits? What do you mean?
Are there patterns that are just inherently impossible to completely remove, even if we allow for recoloring a small portion of the space?
So it's like asking, are there any mathematical fortresses that are completely impenetrable?
Precisely. And exploring these boundaries, understanding which patterns resist our best efforts.
Right.
It will deepen our understanding of how structure and randomness interact in vector spaces.
It's like probing the very nature of mathematical complexity.
Exactly. And it's a journey that I'm really excited to be a part of.
This has been an incredible deep dive expert. Thank you so much for taking us on this journey.
It's been my pleasure. The beauty of mathematics is that there's always something new to discover.
And to our listeners, we hope this deep dive has inspired you to explore the world of mathematics. Further, keep those questions coming and keep diving deep. Welcome back for another deep dive. Today, we're going to be looking at a recent paper that's been causing quite a stir in the world of arithmetic combinatorics. It tackles this fascinating problem of induced arithmetic removal. And specifically, it looks at partition-regular patterns of complexity 1. We've got a whole stack of articles and research notes, and we're here to sort of extract the most important nuggets for you.
Yeah, and what's really exciting about this paper is that it achieves something that was previously thought to be impossible. It's complete removal of these patterns, which is a significant leap forward. It really changes how we understand how we can manipulate and control these really fundamental structures.
Right. And to appreciate that breakthrough, and we need to kind of get a grasp on this concept of partition regularity. It's this wild idea that certain arithmetic patterns are just guaranteed to exist in a set of numbers. It doesn't matter how you try to color them. They're always there.
Yeah. Exactly. Imagine like coloring the integers from 1 to 9 in any way you like. And you can use as many colors as you want, but no matter what you do, you're going to find at least one arithmetic progression of length 3 where all 3 numbers are the same color.
That's incredible. So it's like these patterns are playing a cosmic game of hide and seek, and they always win. So how does this paper manage to make these seemingly unbreakable patterns disappear?
Well, their strategy is this two-step process, which leverages some pretty powerful tools from arithmetic combinatorics. So first, they create a simplified representation of the space where the patterns live. And this is called a regular model. It's kind of like, building a scale model of a city to study traffic flow. And it allows them to analyze the patterns in a more manageable setting.
Okay, so they sort of simplified the playing field. What's the second step?
Well, the second step is where the magic happens. They very carefully select these smaller pieces of the model. These are called subcosets, and these subcosets govern the recoloring process. It's kind of like strategically placing traffic lights at specific intersections in our city model, to control the flow of cars.
I'm starting to see the picture here.
Yeah.
By carefully choosing these subcosets, they can kind of manipulate the coloring of the entire space. And then, poof, those stubborn patterns vanish. But what makes their approach so groundbreaking? How is it different from what people have tried before?
The key difference is this innovative use of multiple subcosets. So previous methods really tried to find one perfect subcoset to represent each larger section of the space. But this approach would run into trouble, especially when dealing with irregular cases, particularly what's called the zero coset.
The zero coset. Why was that such a problem?
Well, the zero coset, which contains the element 0, often behaves in a way that kind of defies those nice, predictable properties that we want in our subcosets. It's like a troublemaker that throws a wrench into the whole system. And previous methods would have to treat it as a special case, which prevented complete removal.
So how did this paper overcome that obstacle?
Well, they realized that instead of searching for that one perfect representative, they could select multiple subcosets within each larger section. It's sort of like having a diverse committee instead of a single leader. And this provides much more flexibility, allowing them to handle those irregular cases more smoothly.
Okay, that makes sense. So it's like they figured out that a team approach is more effective than going it alone. So how do they choose these multiple subcosets? It sounds like they're walking a tightrope here, trying to balance all these different factors.
Yeah, and they actually leverage the property that makes these patterns so persistent in the first place, partition regularity. They use it to define what's called an auxiliary coloring on the set of all possible subcosets.
Wait, an auxiliary coloring. So they're introducing a whole new coloring scheme on top of the original one.
Exactly. But this new coloring, it's not about aesthetics. It's about strategy. The colors in this new scheme actually represent desirable properties that they want their chosen subcosets to have. Things like being regular in the sense of Fourier uniformity and having color densities that align well with the densities of the larger cosets.
So it's like they're tagging the subcosets with labels that indicate how well suited they are for the job.
Precisely. And then by applying this powerful result known as Rado's theorem, but over finite fields, they can find a large number of configurations of subcosets, all of which are monochromatic in this auxiliary coloring.
Monochromatic meaning they all have the same color in this new scheme, which means they all share those desirable properties. It's a pretty ingenious way to exploit the abundance of partition-regular patterns.
Exactly. And that's how they build those committees of subcoset representatives that govern the recoloring process. And by carefully choosing these committees, they gain this very precise control over the color densities throughout the whole space, which ultimately leads to completely removing the pattern.
Okay. This is all incredibly fascinating, but I have to admit, my head is starting to spin a little bit here.
Right.
We've covered a lot of ground. from partition regularity to regular models to multiple subcosets and now auxiliary colorings. Can we maybe take a step back for a second and recap the key takeaways so far?
Absolutely. So the core idea here is that this paper presents a groundbreaking new approach to this problem of induced removal of these partition-regular arithmetic patterns. It hinges on this two-step strategy. First, simplify the space by constructing this regular model. And then second, they leverage the abundance of partition-regular patterns to select multiple well-behaved subcosets that govern the recoloring process.
Right. And this multiple subcoset approach is the real game changer. It allows them to overcome the challenges posed by those pesky irregular cases, like the zero coset, and they achieve complete removal of the pattern for the first time. But before we dive into all the nitty-gritty details of their proof, I think it's important to address the so what question. Why should we care about this seemingly abstract mathematical problem?
That's a great question. So while this particular paper is focused on, the realm of pure mathematics, the techniques and insights that they've developed actually have the potential to ripple outwards into a variety of different disciplines. For example, in theoretical computer science, this work could lead to more efficient algorithms for something called property testing, which is this fundamental problem that involves, quickly determining whether a massive data set possesses a certain property or not.
So instead of having to examine every single data point, we could use these techniques to just kind of quickly sniff test the data and identify any anomalies.
Exactly. And then by efficiently removing those anomalies, you could transform the data set into one that perfectly exhibits that desired property. And this has implications for, data analysis, algorithm design, even machine learning.
Fascinating. So this seemingly abstract mathematical work could actually have real-world implications, improving the efficiency and accuracy of our data-driven algorithms. What other fields might be impacted?
Well, another area where this research could prove to be valuable is cryptography. That's the science of secure communication, of course. And the patterns studied in this paper, they actually have deep connections to this concept of pseudo-randomness, which is essential for designing secure cryptographic systems.
So understanding how to manipulate these patterns could help us build more robust, more secure communication systems. It's like a mathematical arms race between code makers and code breakers.
Exactly. And this paper is giving the code makers some pretty powerful new tools. But beyond these specific applications, the work also has these profound implications for how we understand complexity, randomness, and the limits of predictability. The fact that certain arithmetic patterns are guaranteed to exist, no matter how we try to disguise them, it raises some fundamental questions about the nature of mathematical objects and the very fabric of reality.
It's like peering into the hidden architecture of the universe and discovering these beautiful, inevitable patterns woven into its very essence.
Precisely. And by exploring these patterns, we're not just solving these mathematical puzzles, we're gaining these deeper insights into the fundamental nature of order and chaos.
All right, I think we've laid a pretty solid foundation for understanding the significance of this paper. So now let's roll up our sleeves and delve into the mathematical details of their proof. One of the first things they do is define the concept of an arithmetic pattern formally. They use linear forms and colorings to do this. Could you walk us through that definition?
Sure. So they define an arithmetic pattern, denoted by H, as a tuple, Lx, where L represents a collection of linear forms, say L1, L2, L, and X represents a set of R colorings.
Okay, so let's break that down a little bit. Linear forms are just mathematical expressions involving variables and constants, right? Like 2x plus 3y5 would be a linear form.
Exactly. And in this context, each linear form represents a position within the arithmetic pattern. So for a three-term arithmetic progression, you'd have three linear forms, x, x plus d, and x plus 2.
I see. So the linear forms kind of capture the structure of the pattern. What about those R colorings?
Well, an R coloring is simply a function that assigns one of R colors to each of the M linear forms in L.
So if we have two colors, a monochromatic three-term arithmetic progression could be represented as a single pattern with the linear forms we just mentioned and two constant colorings, one always assigning color 1 and the other always assigning color 2.
Precisely. And this notation allows them to capture both possibilities of a monochromatic three-term arithmetic progression, all three numbers being color 1 or all three being color 2.
That's a clever way to represent it concisely. Now, they introduced this concept of the density of a pattern. What does that mean exactly?
Well, density in this context is basically a way of quantifying how often a particular pattern appears within a given coloring of a space. It's like measuring how concentrated the pattern is. Formally, for a given pattern H and an R coloring of the space, the density of H under is represented as H.
So if a pattern has a high density, it means there are a lot of instances of that pattern within the colored space. And if it has a low density, there are only a few.
Exactly. And this concept of density is crucial in their proof, because their main theorem states that if the density of the pattern in the original coloring is below a certain threshold, then they can find a new coloring that's very close to the original one, and it completely eliminates the pattern.
So if the pattern isn't too prevalent to begin with, they can make it vanish entirely with just a few strategic tweaks to the coloring. It's pretty remarkable. They also mentioned something called a telescoping identity, which sounds a bit intimidating. What's that all about?
Don't worry, it's not as scary as it sounds. This identity is basically a mathematical trick that lets them break down the difference between the densities of two patterns into a sum of smaller, more manageable terms.
So it's like a mathematical tool that helps them dissect the problem into bite-sized pieces.
Exactly. And this leads to another powerful tool they utilize, which is called the arithmetic regularity lemma. This lemma allows them to partition the space into these smaller, well-behaved pieces called cosets, where the coloring behaves in a more predictable way.
Right. They mentioned these cosets are characterized by a property called Fourier uniformity. Can you explain what that means? In a way that even I can understand.
Imagine you have a function that represents the coloring of the space. Fourier uniformity is basically a measure of how smooth or how random that function is within a coset. If a function is highly Fourier uniform, it means the colors are kind of distributed in a way that resembles a random assignment. But if it has low Fourier uniformity, it suggests there's some underlying structure or bias in the coloring.
So the arithmetic regularity lemma helps them divide the space into these cosets, where the colors are either randomly scattered or exhibit some kind of organized pattern. It's like creating order out of chaos.
Precisely. And by applying this lemma, they can focus their analysis on the cosets, where the coloring is not too wild or erratic, making the problem much more manageable.
Okay, that makes sense. Now, they bring up this concept of true complexity, which seems to play a really crucial role in all of this. What does it mean for a system of linear forms to have a certain true complexity?
So true complexity in this context of linear systems, it captures how intricate the relationships are between the variables in the system. It's basically a measure of how difficult it is to predict the values of some variables based on the values of others.
So high true complexity suggests the variables are all tangled up in this really complex way. And low true complexity implies there are simpler relationships.
Exactly. And this paper specifically focuses on linear systems with true complexity 1, meaning they're relatively straightforward to analyze. For example, the system x plus d, x plus tumor, which represents the three-term arithmetic progression, has a true complexity of 1. But if we add another term, x plus d, x plus second, x plus third, the true complexity increases.
Interesting. So why is true complexity so important in the context of these induced removal lemmas?
Because it directly impacts our ability to count the number of instances of the pattern it represents. We can only effectively count instances of patterns that come from systems with low true complexity. That's why this paper focuses on patterns of complexity 1, because it lets them apply this powerful tool called the counting lemma.
Ah, the counting lemma. What's that all about?
The counting lemma is this key result that lets us estimate the number of solutions to a linear system within a set of numbers. And it does this based on the properties of the individual cosets that we get from that arithmetic regularity lemma. In essence, it tells us that if the cosets are well-behaved, meaning they're Fourier uniform, and they satisfy a property called coset consistency, then the number of solutions within those cosets is roughly what we would expect if the numbers were just assigned randomly.
Coset consistency. What does that mean exactly?
Well, it's basically a condition that ensures that the arrangement of the cosets kind of aligns with the structure of the linear system. Think of it like this. If we're looking for three-term arithmetic progressions within a set of cosets, then those cosets themselves need to form an arithmetic progression for any solutions to exist. So that's coset consistency in a nutshell.
So it's like making sure the pieces of the puzzle fit together in a way that makes sense for the pattern we're looking for.
Precisely. And the counting lemma gives us a way to estimate the number of solutions based on the density of the pattern within these consistent, well-behaved cassettes.
Okay, I think I'm starting to see how all these pieces are fitting together now. We've got the concept of partition-regular patterns, which we know are abundant. We use the arithmetic regularity lemma to break down the space into these manageable cosets, characterized by Fourier uniformity. And for patterns of complexity 1, we can apply the counting lemma to estimate the number of pattern instances within consistent cosets.
You've summarized it beautifully. And now, with those tools in hand, we can really dive into the heart of their proof. which involves this clever strategy for selecting very specific subcosets to achieve the complete removal of those patterns. But maybe we should pause here and continue this in the next part of our deep dive. I think this stuff is pretty dense.
I agree. It's a lot to digest. Let's take a break and come back refreshed and ready to tackle those details of their proof.
Welcome back to our deep dive into this fascinating world of induced arithmetic removal. Last time we were talking about those intricate mathematical concepts of partition-regular patterns and things like coset consistency and the power of that counting lemma.
Yeah, we really got down into the weeds there, exploring how this innovative paper achieved that complete removal of these patterns, which had been like a real sticking point for mathematicians for a while.
Yeah.
It's pretty wild how they came up with this whole system of multiple subcoset representatives to deal with that tricky non-regular zero coset.
It's a very ingenious strategy. And now that we have all the core concepts, fresh in our minds and the general structure of their proof, let's dig into the heart of their argument. They begin by outlining this key proposition, which they call intermediate subcoset selection. And what this proposition does is it gives them a method for finding a first set of subcosets that have some good properties, but they don't quite give them the full level of control they need for complete removal.
So it's like a stepping stone toward their ultimate goal.
Exactly. This intermediate step helps them identify those subcosets that are regular, meaning they have that nice Fourier uniformity property, and where the color densities are close to the densities of the larger cosets that they represent.
So they're starting to narrow down the possibilities, kind of honing in on those subcosets that are well-behaved and informative.
Precisely. But this initial selection doesn't quite get them all the way there. They still need to refine this selection further to achieve complete control over that zero coset. And that's where their main innovation comes in, what they call the selecting multiple subcosets lemma.
Right. They need some way to find even more specialized subcosets within the ones they've already identified. Mm-hmm. What's the key idea behind this lemma?
Well, the heart of this lemma is to leverage the abundance of those partition-regular patterns, the ones that are guaranteed by Rado's theorem. And they do this to carefully select not just one, but multiple subcosets within each of those initially chosen cosets.
So this is where that committee of subcoset representatives comes in. But how do they actually choose these multiple subcosets?
They define what we call an auxiliary coloring. It's on the set of all possible subcosets. And the colors, so to speak, in this scheme, they represent the desirable properties that they want these subcosets to have. Properties like being regular and having densities that closely align with the densities of their parent cosets.
Okay, so it's like a clever coding scheme where they're tagging the subcosets with labels that indicate how well suited they are for the task at hand.
Precisely. And then they apply Rado's theorem to this auxiliary coloring scheme. And remember, Rado's theorem guarantees that they'll find a large number of what we call monochromatic configurations within this scheme, meaning, sets of subcosets that all share those desirable properties.
So those monochromatic configurations become their committees of subcoset representatives. It's a pretty clever way to kind of exploit the abundance of these partition-regular patterns to their advantage.
Exactly. And this is how they construct those committees of subcoset representatives that govern the recoloring process. And by very carefully choosing these committees, they get that precise control over the color densities, throughout the entire space, which eventually leads to the complete removal of the pattern.
Okay. I think I'm starting to see how all the pieces fit together. So they've outlined this process of selecting multiple subcosets. They do that using that auxiliary coloring and Rado's theorem. But how does this actually translate into a concrete recoloring scheme for the original space? They talk about a recoloring lemma that kind of formalizes this. What's that all about?
Yeah, the recoloring lemma is really the bridge between those carefully chosen subcoset committees and the actual recoloring of the original space. It essentially provides a recipe for creating a new coloring that's very close to the original, but eliminates the targeted patterns.
So we're tweaking that original coloring just a tiny bit, guided by the wisdom of those subcoset committees. What's the key property of this new coloring?
Well, the key here is that in this new coloring, if a color appears within a larger coset, then it must also appear with a sufficiently high density within all the chosen subcosets that represent that larger coset.
Oh, okay. I see. So it's like making sure that the colors present in the larger coset have strong support from their subcoset representatives. Like, no color gets to be in the big leagues without having earned its stripes in the minors, so to speak.
Exactly. And this property is really crucial because it allows them to apply that counting lemma effectively. Remember, the counting lemma helps us estimate the number of pattern instances within those well-behaved cosets. And by ensuring this connection between the color densities in the larger cosets and their subcoset representatives, they can control the overall density of the pattern throughout the whole space.
So it's like they've set up this system where the color densities in those carefully chosen subcosets, they kind of dictate the fate of the pattern in the larger cosets and ultimately the entire space. It's all connected.
Precisely. And this leads us to the kind of climax of their proof, which is the final theorem that demonstrates that complete removal is possible using this approach.
I'm on the edge of my seat. Let's hear it. How do they put all of these pieces together to prove this really remarkable result?
Okay. The theorem states that for any partition-regular pattern of complexity 1, there exists a threshold density. And if the density of the pattern in the original coloring is below this threshold, then we can find a new coloring that's very close to the original and completely eliminates the pattern.
So if the pattern isn't too prevalent to begin with, they can make it vanish entirely with just a few strategic tweaks to the coloring.
Exactly. And the proof hinges on applying that recoloring lemma to get a new coloring that satisfies that crucial density property we just talked about. And then they assume, for the sake of contradiction, that there is still an instance of the pattern lurking in this new coloring.
It's like they're saying, okay, let's assume for a moment that this pattern is stubborn enough to survive our clever recoloring. Let's see where that assumption takes us.
Precisely. And by carefully analyzing the properties of the chosen subcosets and using that counting lemma, they show that this assumption leads to a contradiction.
So the very existence of a pattern instance in the new coloring breaks the rules of the system they've carefully constructed.
Exactly. And this contradiction means that their initial assumption must be false, right? There can't be any instances of the pattern remaining in that new coloring. They've achieved complete removal.
Wow. It's a really elegant and powerful result. By combining this kind of intricate dance of subcoset selection and density control and that strategic use of the counting lemma, they've proven something truly remarkable.
Indeed, it really is a testament to the power of abstract mathematical thinking, to unlock these deeper truths about the world around us.
Okay, I think I'm following the logic of their proof, but I have to admit, those mathematical details are pretty dense. Could we maybe walk through some of the key steps in a bit more detail? For example, how do they connect this concept of partition-regular patterns, which are defined in terms of matrices, to those linear systems we've been discussing?
Sure. So that connection is really crucial for understanding how they apply Rado's theorem to their specific problem. They start by reminding us of this key result known as Rado's column conditions. And these conditions basically give us a way to determine whether a matrix is partition-regular or not.
So it's like a checklist of properties that a matrix needs to have to qualify as a partition-regular matrix. What are those conditions?
Essentially, they tell us that a matrix, we'll call it A, is partition-regular if we can rearrange its columns and group them into sets in a way that satisfies these two things. One, the sum of the columns in the first set is 0, and 2, the sum of the columns in each subsequent set can be expressed as a combination of columns from the preceding sets.
Okay, so there's a very specific structure to these matrices that guarantee that they'll lead to these partition-regular patterns.
Exactly. And they emphasize this, what we call quantitative version of Rado's theorem over finite fields. And this version tells us not only that those partition-regular matrices lead to patterns that always exist, but it also gives us a lower bound on how many of these patterns we can actually find within a colored space.
So it's not just a qualitative statement. It also provides a quantitative measure of the abundance of these patterns. That's pretty powerful. But how do they actually apply this theorem to those patterns that are defined by those linear forms?
Right. So they introduce two key matrices, which they call ML and KL. And these matrices capture the essential information about a system of linear forms, L. So ML is essentially a matrix representation of the coefficients of the linear forms, while KL is built from the relationships or the dependencies between those forms.
So ML gives us the building blocks of the linear forms, and KL tells us how those blocks kind of fit together.
Precisely. And they show that the solutions to this equation, KO is 0, 0, correspond exactly to the values that that linear system L can take. In other words, KL captures all of the possible combinations of values that satisfy those linear forms in L.
Okay, I see. So by analyzing KL, we're essentially analyzing all the possible instances of the pattern that's defined by those linear forms in L.
Exactly. And they use this connection to define what it means for a linear system to be partition regular. They say that L is partition regular if and only if that matrix KL satisfies those Rado's column conditions that we talked about before.
So by checking those conditions on KL, we can figure out whether the corresponding linear system is going to generate a pattern that's guaranteed to show up, like a partition regular pattern.
You got it. And this connection between the linear systems and matrices is crucial because it allows them to apply that quantitative version of Rado's theorem, to find those abundant, consistent subcoset configurations that are kind of the fuel for their modified strategy.
It's all starting to click now. So they've laid out the mathematical groundwork. They've defined all these key concepts, and they've established all those connections between matrices, linear systems, and partition regularity. Now, let's dive into the heart of the proof, where they actually implement this new subcoset selection technique and then prove that it leads to that complete removal.
Right. So they begin by reminding us about this fundamental concept in linear algebra called the orthogonal complement of a subspace. And essentially, if we have a subspace, which we'll call H, that's within a larger vector space, its orthogonal complement, denoted H, is the set of all vectors that are perpendicular to every vector in H.
Okay. It's like imagining a line in 3D space. Its orthogonal complement would be that plane that's perpendicular to that line, the one containing all the vectors that make right angles with it.
Exactly. And they use this concept to express the indicator function of a subspace in a very clever way. The indicator function, for those who might not be familiar, is simply a function that takes on the value 1 for elements within the subspace and 0 for elements outside of it.
So it's like a mathematical membership card, right?
Yeah.
It tells you whether an element belongs to the club or not.
Precisely. And they show that we can express this indicator function using a sum of exponential terms, essentially leveraging the properties of the Fourier transform. This might sound a bit complicated, but it's a standard technique in this area of math.
Right. We talked about Fourier transforms earlier, those tools that help us analyze the frequency components of signals or functions. It seems they're using them here to kind of dissect the structure of these subspaces.
Exactly. And by expressing the indicator function in this way, they gain this foothold for analyzing the behavior of functions within those carefully chosen subcosets. They show how this representation allows them to relate the average value of a function on a smaller subcoset to its average value on a larger coset that contains it.
So they're building a bridge between the properties of these nested cosets, right? They're linking the behavior of functions at different levels of this hierarchy.
Precisely. And this connection is absolutely crucial for establishing the properties of their recoloring scheme. They need to make sure that the colors that are present in the larger cosets are well represented in those subcoset committees that they chose.
Okay, I'm starting to see how the pieces fit together. They're using the properties of those orthogonal complements and Fourier transforms to analyze how functions behave on different levels of this coset hierarchy, which ultimately allows them to control the color densities and ensure that their recoloring strategy works. It's a lot of technical machinery, but the logic behind it is pretty clear.
You got it. And with that technical foundation in place, they can move on to define the recoloring scheme formally and then prove that it leads to the complete removal of those partition regular patterns.
Let's get to those details. How do they actually construct this recoloring scheme? It sounds like they're doing this delicate balancing act to make sure that the new coloring is similar to the original one, but also gets rid of those pesky patterns.
It is a delicate balancing act. They start by applying that intermediate subcoset selection proposition, which we discussed earlier, to find that first set of well-behaved subcosets. And those subcosets are regular, meaning they have that nice Fourier uniformity property, and their color densities are close to the densities of the larger cosets they represent.
Okay, so it's like they're sketching out the initial contours of the recoloring by identifying these promising subcosets.
Exactly. And then they apply their key innovation, the selecting multiple subcosets lemma, Remember, this lemma uses the abundance of partition-regular patterns, as guaranteed by Rado's theorem, to find multiple subcosets within each of those initially chosen ones.
Right. It's like they're saying, okay, we found some good candidates, but let's put together a whole team of representatives to make sure we have complete control over the situation.
Precisely. And they choose these kind of subcoset committees by defining that clever auxiliary coloring scheme where the colors represent those desirable properties they want the subcosets to have. And Rado's theorem makes sure they'll find enough of these desirable configurations to cover the whole space, including that troublesome zero coset.
Okay, so they've assembled their all-star teams of subcoset representatives. Now, how do they actually use these committees to recolor the space?
Here's where the strategy gets really intricate. They define a set of rules, essentially, for how to recolor each larger coset based on the properties of its chosen subcoset representatives. So for each larger coset, they figure out what we call a dominant color. It's the color that has a high density in at least one of its subcoset representatives.
So each subcoset gets to vote on their favorite color, and the color with the most support wins.
Exactly. And then they recolor any elements within that larger coset that don't already have that dominant color. The key here is that they only recolor elements that belong to colors that have a low density within all of those chosen subcoset representatives.
So it's a very targeted approach to recoloring. They're only changing the colors of elements that aren't already well represented by their subcoset committees.
Exactly. And this ensures that the new coloring remains close to the original one because they're only tweaking a small percentage of the elements. But at the same time, this strategic recoloring significantly changes the overall densities of the colors within those larger cosets.
And that's what eventually leads to removing those patterns. By manipulating the color densities, they're disrupting that delicate balance that allows those patterns to exist in the first place.
Exactly. And to prove that this recoloring scheme actually achieves complete removal, they do a proof by contradiction. They start by assuming, just for a moment, that there's still an instance of the pattern hanging around in this new coloring.
It's like they're saying, okay, let's entertain the possibility that our fancy new scheme hasn't completely wiped out the pattern. Let's see where that takes us.
Precisely. And they carefully analyze this hypothetical pattern instance, tracing it back to the chosen subcoset representatives. And they use the counting lemma, along with the carefully crafted properties of that recoloring scheme, to show that this assumption actually leads to an impossible situation.
So the very existence of a pattern instance in this new coloring, it violates the rules of the system they've created. It's like a mathematical paradox.
Exactly. And this contradiction forces them to conclude that their initial assumption has to be false. There can't be any instances of the pattern still hanging around in that new coloring. They've done it. They've achieved complete removal.
Wow. That's a really clever and satisfying conclusion to this very intricate argument. They've brought together so many threads here: partition regularity, subcoset selection, color density manipulation, and the counting lemma. And they've woven them into this elegant tapestry of mathematical proof.
It's a beautiful example of how that kind of abstract mathematical thinking can unlock these profound insights and solve problems that seem really hard to crack.
Okay. I think I'm with you on the logic of their proof, but I have to admit, the mathematical details are pretty dense. Could we maybe go through some of the key steps in a bit more detail? Like, for example, how do they connect this idea of partition-regular patterns, which are defined using matrices, to the linear systems we've been talking about?
Yeah, absolutely. That connection is super important for understanding how they use Rado's theorem for their specific problem. They start by reminding us about this key result, which is known as Rado's column conditions. And these conditions basically provide a way to determine whether a matrix is partition regular or not.
So it's like a checklist of properties that a matrix needs to have to be considered partition regular. What are those conditions?
Essentially, they tell us that a matrix, we'll call it A, is partition regular if we can rearrange its columns and group them into sets so that they satisfy these two things. One, the sum of the columns in that first set has to be 0. And 2, the sum of the columns in each of the subsequent sets can be expressed as a combination of columns from the sets that came before it.
Okay, so there's this very specific structure to these matrices that ensures they're going to lead to partition-regular patterns.
Exactly. And they emphasize this, what we call a quantitative version of Rado's theorem over finite fields. And this version tells us not only that those partition-regular matrices lead to patterns that always exist, but it also gives us a lower bound on how many of these patterns we can actually find within a colored space.
So it's not just saying, yeah, these patterns exist. It's giving us a way to measure how many of them are out there. That's really powerful. simple. But how do they actually apply this theorem to patterns that are defined by these linear forms?
Well, they introduced these two key matrices called ML and KL. And these matrices capture the essential information about a system of linear forms, which we'll call L. So ML is basically a matrix representation of the coefficients of the linear forms, while KL is built from the relationships or dependencies between those forms.
So ML gives us the building blocks of those linear forms, and KL tells us how those blocks sit together.
Precisely. And they show that the solutions to this equation, KL equals 0, correspond exactly to the values that that linear system L can take. In other words, KL captures all the possible combinations of values that satisfy the linear forms in L.
Okay, I see. So by analyzing KL, we're essentially analyzing all the possible instances of the pattern that's defined by those linear forms in L.
Exactly. And they use this connection to define what it means for a linear system to be partition-regular. They say that L is partition-regular if and only if that matrix KL satisfies Radau's column conditions.
So by checking those conditions on KL, we can figure out whether the corresponding linear system is going to generate a pattern that's guaranteed to show up, like a partition-regular pattern.
You got it. And this link between linear systems and matrices is crucial because it allows them to apply that quantitative version of Radau's theorem, to find those abundant, consistent subcoset configurations. They're the fuel for their strategy.
It's all starting to click now. They've laid out the mathematical groundwork, they've defined the key concepts, and established the connections between matrices, linear systems, and partition regularity. Now let's dive into the heart of their proof, how they actually implement this new subcoset selection technique and prove that it leads to complete removal.
Okay, so they start off by reminding us about this kind of fundamental concept in linear algebra. It's called the orthogonal complement of a subspace. And essentially, if we have a subspace, let's call it H, which is inside a bigger vector space, its orthogonal complement, we'll call it H, is the set of all vectors that are perpendicular to every vector in H.
Okay, so it's like imagining, say, a line in 3D space. Its orthogonal complement would be the plane that's perpendicular to that line, the plane that contains all those vectors that are making right angles with it.
Exactly. And they use this concept to express what we call the indicator function of a subspace. They do it in a really clever way. And that indicator function, for those who might not be familiar, is simply a function that takes on the value 1 for elements within that subspace and 0 for elements outside of it.
So it's like a mathematical membership card. It tells you if an element belongs to the club or not.
Precisely. And they show that we can express this indicator function using a sum of these exponential terms. So essentially, they're leveraging the properties of that Fourier transform. This might sound a bit complicated, but it's a pretty standard technique in this area of math.
Right. We talked about those Fourier transforms earlier, remember? Those tools that help us analyze those frequency components of signals or functions. It seems they're using them here to kind of break down the structure of these subspaces.
Exactly. And by expressing that indicator function this way, they get a foothold for analyzing how functions behave within those carefully chosen subcosets. They show how this representation lets them relate the average value of a function on a smaller subcoset to its average value on a larger coset that contains it.
So they're building a bridge between the properties of those nested cosets. They're connecting how functions behave at different levels of this hierarchy.
Precisely. And this connection is absolutely crucial for establishing the properties of their recoloring scheme. They need to make sure that the colors that are present in the larger cosets are well represented in those subcoset committees that they chose.
Okay. I'm starting to see how everything fits together. They're using the properties of orthogonal complements and Fourier transforms to analyze how functions behave on different levels of that coset hierarchy. And that's what ultimately lets them control those color densities and make sure their recoloring strategy works. It's a lot of technical stuff, but the logic behind it is pretty clear.
You got it. And with that technical foundation in place, they can move on to define the recoloring scheme formally. And then they prove that it leads to the complete removal of those partition-regular patterns.
Welcome back. We've been on this incredible journey, haven't we, through the world of induced arithmetic removal, exploring how this paper managed to pull off complete removal of those partition-regular patterns, the ones with complexity 1.
Yeah, it's been quite a ride through this really abstract mathematical landscape. But, it's got those surprising connections to the real world, too, which is always exciting.
Right. Last time we left off talking about the heart of their proof, this sort of intricate dance of subcoset selection and how they manipulate color densities. And of course, that strategic use of the counting lemma.
Yeah, and how they cleverly connected those partition-regular patterns, the ones defined by matrices, to the linear systems that control the structure of those patterns. It was a pretty neat trick.
Absolutely. Yeah. They use those matrices, ML and KL, to translate the properties of those linear systems into something they could actually work with. And that's how they applied Radau's theorem, right? It was the key to guaranteeing the existence of all those subcoset configurations they need for their strategy.
Spot on. It's a perfect example of how connecting different parts of math can lead to some really groundbreaking discoveries.
But I'll be honest, I'm still a little fuzzy on some of the technical details of how they actually build this recoloring scheme.
Yeah.
And how they prove that it really does lead to complete removal.
Okay, no problem. Let's break it down. Remember, they start with that intermediate subcoset selection proposition to find that first group of well-behaved subcosets, the ones that are regular, meaning they have that Fourier uniformity property, and where the color densities are close to the densities of those bigger cosets they represent.
Right, so it's like they're zeroing in on the subcosets that are the best fit for what they're trying to do.
Exactly, but that initial selection is just the first step. They've got to refine it even more to get complete control over that zero coset. That's where their big innovation comes in, the selecting multiple subcosets lemma.
Ah, yes. That's where they use Radau's theorem to create those committees of subcoset representatives. I remember that. But how do those committees actually tell them how to recolor everything? That part is still a bit of a mystery to me.
It's a little tricky, but let me see if I can explain it. They basically create a set of rules for how to recolor each larger coset. And those rules are based on the properties of the subcoset representatives that they chose. So for each larger coset, they find what they call a dominant color. It's the one that shows up a lot in at least one of its subcoset representatives.
So it's like each subcoset gets to vote for its favorite color, and the one with the most votes wins.
Exactly. Then they take any elements within that larger coset that don't already have that dominant color, and they recolor them. But here's the catch. They only recolor the elements that belong to colors that have low density in all of the chosen subcoset representatives.
Okay, so it's very targeted, this recoloring. They're only changing things that aren't already well represented by those committees they set up.
Exactly. And that's how they make sure the new coloring isn't too different from the original one. They're really only tweaking a small number of elements. But, and this is the important part, this recoloring ends up changing the overall density of the colors within the larger cosets in a big way.
And that's what ends up getting rid of the patterns, right? By messing with those color densities, they mess up that balance that lets those patterns exist in the first place.
Right on. And to prove that this recoloring scheme really does get rid of the patterns completely, they use a proof by contradiction. So they start by assuming that there's still a pattern instance hiding out in this new coloring.
It's like they're saying, okay, let's just pretend for a second that our super clever plan didn't actually wipe out the pattern. Where does that lead us?
Yes. And they take this hypothetical pattern instance and carefully trace it back to those chosen subcoset representatives. And they use the counting lemma and those carefully chosen properties of the recoloring to show that this assumption leads to something impossible.
So the very fact that there's a pattern instance in this new coloring, it breaks the rules of the system they put together.
Like a mathematical paradox, right?
Exactly. And that contradiction means that their initial assumption has to be wrong. There can't be any of the pattern left in that new coloring. They've achieved complete removal.
It's a really clever ending to this complicated argument. They've pulled together so many different ideas: partition regularity, subcoset selection, color density manipulation, the counting lemma, and it's all woven together into this elegant mathematical proof.
It's a beautiful example of how abstract math can uncover some really profound insights and solve problems that seemed, unsolvable. This has been an incredible journey through some pretty complex math. We started with the basics of partition regularity and arithmetic patterns and ended up diving deep into subcoset selection, Fourier uniformity, the counting lemma. It's been quite a deep dive.
And we saw how all those abstract concepts could be used to create a powerful and elegant proof that gets a truly remarkable result.
It just goes to show the power of human curiosity and the incredible things we can do when we push the limits of what we understand about math.
Couldn't have said it better myself. And even though this paper focuses on a really specific problem in arithmetic combinatorics, the ideas they're exploring have implications for other areas too. Think about computer science, cryptography, even our understanding of patterns and randomness in general. This work opens up a whole new world of possibilities.
Reminds us that even the most abstract math can have a big impact on the world around us, and that chasing after knowledge, just because we're curious and love to discover new things, can lead to breakthroughs that change the way we see the universe and our place in it.
Couldn't agree more. And I think that's a great place to wrap things up for today. Thanks for joining us on this deep dive. Until next time, keep exploring, keep asking questions, and keep pushing the boundaries of what's possible.
And never forget the power of a good math puzzle.